We're going to continue heterogeneous systems today. But as we mentioned yesterday, one of the things specialized systems or heterogeneous systems enables is accelerating bottlenecks. So I titled this bottleneck acceleration because it's a more general concept than heterogeneity, but we're going to use the notion of heterogeneity to clearly accelerate bottlenecks. And we're going to look at especially the bottlenecks that exist in multi-threaded applications in this case, some of which you're already familiar with, based on the discussion we had in parallel application memory scheduling. Do people remember that? Okay, good. But clearly there are bottlenecks that exist in other parts of systems, but you can use similar techniques for accelerating those bottlenecks also. So even if you have a single-threaded program, if you can understand what part is more critical than what other parts, you can use heterogeneity to speed up that part that's bottlenecking your execution. Right? You may have a piece of code that's extremely slow for whatever reason, pointer chasing, for example, and you may actually have a specialized core for pointer chasing purposes. Right? Clearly, this idea is much more general, right? But we're going to examine bottlenecks in parallel applications, and this is what we were doing. And okay, remember this picture. There's a lot in this slide, but these are very fundamental. There are three major. There's clearly the serial bottleneck, which we talked about accelerating using an asymmetric multi-core processor, right? You have a large out-of-order, heavy core that's good at executing serial code. When you get to the serial bottleneck, why don't you ship the code there? But we also discussed that parallel portion is not perfectly parallel for three major reasons, three fundamental reasons. Has anyone come up with a new reason? Not yet? Okay. I'll wait. I'm happy to hear a new reason that doesn't fall into these three categories: synchronization, load imbalance, resource sharing. And because of this, you can become serialized relatively easily in different parts of the program. And I'll give you examples of this. We already saw one example from MySQL, for example, right, yesterday. And this is what we were talking about when we parted yesterday. Basically, we have serialized or imbalanced execution in the parallel portion of a program. And this could also benefit from a large core. In this case, I'm talking about a large core. It's more general purpose. But clearly, you can specialize this core for execution of different types of code also. In fact, in extreme form of heterogeneity, you would map different types of critical sections to different cores that can execute those critical sections in the best way, right? A large core is not necessarily the most efficient way of executing a piece of code. Ideally, you would bake in that piece of code into some logic, right? You would have an ASIC that executes that. We're not talking about that one. So you can be a lot more energy efficient than what we're going to describe. So examples are critical sections that are contended and parallel stages that take longer than others to execute. And we were going to dynamically identify these code portions that cause serialization and execute them on a large core. Basically prioritize them somehow, accelerate them somehow. So executing them on a large core is one way of accelerating them. Prioritizing them in the memory scheduler is another way of accelerating them. Prioritizing them in the cache is another way of accelerating them. Ideally, we would like to do all of that, right? Because this is really the critical part of your code. The rest is not critical, at least at the moment. So maybe you should really be focusing all of your resources to get this code done quickly so that it doesn't become the bottleneck anymore. Okay, and this is where we left off, actually. We're going to talk about this work that was published actually 10 years ago now. Technically more than 10 years, because SPOS happens in October. That talks about accelerating critical sections. And the motivation is essentially what we looked at before. So I'm going to motivate in a slightly different way. I like the sort of pure examples in a sense. So what we're going to see is this is time units on the x-axis. This is number of processors used to execute the code. And we're going to assume that you have a piece of code that consists of 12 iterations, and 33% of the instructions are inside the critical section. If you execute this code, and we're going to denote it this way, basically red parts are critical section, gray parts are parallel, executed in parallel in different processors, and this is the idle part. So if you execute this code in a single processor, 33% of each iteration is in the critical section, the rest is parallel, but of course there's no parallelism here that's exploited by multiple processors because you have only one processor. So the execution looks like this, basically. And then if you parallelize this code across two processors, the execution looks like this. Basically, critical sections cannot be executed in parallel. Only one processor can't be in the critical section at a given time, but parallel parts can overlap. You can see that there's some weighting that happens, but mostly it's parallelized now because there's overlap between the critical section and the non-critical section, right? So you actually improve performance by almost 2x. That's good. because you can overlap the latency of the critical section here. Okay, let's go to 3 processors. It looks like this. Now it's becoming difficult to overlap the latency of critical sections, right? You can see that there's some weighting that's happening. But still, there's no weighting that's happening in this part of the code. So again, you improve performance. You almost get a speed up that's close to 3x in this case. But it's, of course, not exactly 3x because of this weighting that happened over here. Okay, now if you go to 4 processors, you don't gain performance anymore. This is assuming that there's no additional communication that's caused by communicating the critical section, shared data, and locks. In real life, actually, you lose performance because there's additional delay that's caused because you need to communicate the shared data and locks between the processors. This is a purist example that doesn't take that into account. But even if you don't take into account that one, now you're limited by the critical sections, right? So you don't gain performance by adding 1 more processor to 3 processors, because if you look over here, at any given point in time, there was a thread that was in the critical section. Meaning that if you add 1 more processor, you're just going to add more weighting, because there's not enough parallelism to cover that critical section anymore. That's the idea. Does that make sense? So this is basically Amdahl's law put in a different way. Going from 3 to 4, you don't gain any performance, you just add more weighting. And in fact, you lose performance in a real system because now you need to communicate shared data and locks between 4 processors as opposed to 3. Okay. So, let's just now this is one example. Let's assume that we accelerate the critical section by 2x. What happens? Again, magically accelerate this by 2x. So the red parts will clearly go down by half, right? And the execution will look like this over here. You don't gain a whole lot here, but still it's a lot. Like 2 out of 10 units is gone. Okay, that's good. Now if you reduce this by 2x, you gain some over here. That's good. Basically, it's compared to this, you get 2x again over here. If you reduce this by 2x, the red parts by 2x, you gain a little bit more over here. But now if you look over here, you're not bottlenecked by critical sections anymore. Meaning, here, if you add 1 more processor, you would add some more critical section, but you can overlap the latency with some parallel parts. So that's the benefit of accelerating critical sections. You're shortening them. As a result, you're improving scalability of the application. Scalability means the number of threads you can execute, you can add the maximum number of threads you can execute this application with that leads to the highest performance. Before it was 3, now it became 4 if you accelerate the critical section by 2x. Make sense? Basically, we're accelerating a parallel bottleneck over here. As a result, going from 3 to 4 processors, you still gain performance. So basically, that's the takeaway. With this simple purist example, accelerating critical sections increases performance, clearly performance over here, but also scalability of the program, meaning the maximum number of threads that lead to the highest performance for the execution of the program. Okay, you can do this example. Clearly, you can parameterize this and you can come up with nice equations with this, but we're not going to do that. But in the end, it's Amdahl's law. Okay, so basically, this is the impact of critical sections on scalability. Contention for critical section leads to serial execution of threads, and that increases with the number of threads, and that limits scalability. As you keep adding threads or adding cores, the contention increases, and also the communication that you need to do for the shared data and locks increases. As a result, you get a picture that looks like this that we discussed last time. You saw this picture. That's why your performance reduces. Your contention increases, and the communication between the processors increases. But if you have an asymmetric core, as I said, we're going to go to a curve that looks like this. And you can actually do better than this, but this is 10 years ago, 11 years ago. Later works has improved that and made it more scalable. Okay, so basically, this is the case for asymmetry here. I think it's obvious by now. You have these sequential parts of a program, which could be sequential bottleneck, the critical sections, or limiter stages. And they really must be short if you want high scalability and high performance. As we discussed briefly yesterday, you can say, okay, this is not my problem as a system designer, this is the programmer's problem. That's not a good approach, because once you take that stand, you will not have a very good product that is good for everyone in the world, right? Remember the cell processor, for example. I gave that example yesterday. They said, coherence is not our problem, it's the programmer's problem. If you take that approach, then you will have a system that's very difficult to program. And in the end, you're designing these systems so that they're useful, right? If they're not useful for the programmer, if only a very small fraction of the programmers can program the system, they may not be as useful as they could be, right? So clearly you can say programmers should do it, but in general, it's very difficult for the programmers to do this sort of optimization. So the example that I give you over here is from a database, and they're database companies that really dedicate very, very expert programmers to optimize this sort of critical sections. And they know the database in and out. They've been working on it for 30 years or more sometimes. But even they make mistakes, actually. Whenever they go and change the code so that they can reduce the critical section, they may forget to protect some shared data, for example, and they get bugs. And these bugs are very, very difficult to find. That's the performance versus bug trade-off, correctness trade-off. There's a trade-off between performance versus correctness. So these are expert programmers. Now, if you say, okay, all of the programmers should do that, programmers don't necessarily have domain-specific knowledge very well, right? A lot of people program in very high-level language, and they may not know what they're dealing with. So that's something that you should not really rely on. Also, even if the programmer optimized the code for one hardware platform, if you go to some other hardware platform, now the locks are different, the communication is different, latencies are different. So your optimizations may not be the best for that hardware platform. So you have this variation. Clearly, you have limited resources. Do you really expend the programmer's effort to really optimize this program, or do you really expend the programmer's effort on features, right? If you remember Stefan's prefetching talk, he was saying programmers spend time on features, right? That's a different mindset. You could argue that they should not be, but most people in the world are not educated like you in a sense. They're not comfortable across the software hardware stack, right? Most people know only software. They don't even know how a machine works internally. I think it's a bit sad, but that's how you can get high productivity in the end. And you cannot expect those most people, most of the world, to actually go and dedicate their resources to actually optimize these critical sections in the end. I think that's nature. And finally, we discussed that there's a trade-off between performance and debugging, or you can think of it as performance and correctness in the end. As you try to increase the performance of a code, you start making mistakes, and that leads to either more debugging overhead or some bugs that sneak into the field. And that becomes very difficult, of course. Okay, basically the goal is really having a mechanism to shorten the serial bottlenecks without requiring programmer effort. Then, of course, what is the idea? I think the idea is very simple. You accelerate these serialized code sections by shipping them to powerful cores and asymmetric multiprocessor. The question is, how do you do that, of course, right? So what I'm going to describe to you is really a software-hardware cooperative solution in the end. You could potentially implement this purely in hardware. I think it's a bit difficult because you need to really figure out what are the critical sections, for example. We will see how we communicate that through the software. At the software level, you have information about critical sections. Once you go to the hardware level, you lose that because they get, if you remember, we briefly discussed, they get converted into virtual memory addresses and memory locations in the end, load and store instructions. We basically want to communicate more rich information from the software to the hardware such that the hardware can recognize what is a critical section, what is a potential bottleneck. Okay, so the idea is hardware and software cooperatively shipped critical sections to a large, powerful core in an asymmetric multi-core architecture. And what is the benefit? Let's talk about the benefits first. Clearly, this reduces serialization due to contended locks. It reduces the performance impact of hard-to-parallelize sections, and programmer doesn't need to now heavily optimize parallel code. It leads to hopefully fewer bugs and improved productivity. Because the hardware is doing the job for them. Right? You could think of this as hardware accelerating the program for the programmer. If the programmer spent enough time, they would probably reduce the size of the critical section at some point. Now, that's not always true, because sometimes you cannot reduce the size of the critical section, but it can still be contended, and this mechanism is still helpful. Okay, so let's take a look at it. Basically, at the high level, you have a code that looks like this. You enter some critical section, you do some work inside the critical section, and you leave the critical section. And this is our asymmetric multi-core processor. And what we're going to do is add a critical section request buffer to a large core. You can think of this large core as a server. So this is really, in the end, a remote procedure call, remote function call-based programming model. This is a server. These are clients. And this server serves the critical sections. And clients ship the critical sections to the server. Right? This is, it's very similar to distributed system programming model. It's a distributed system on a chip, again, if you want to think about it that way. You're shipping some function calls over here. Of course, generalizing the idea, you can ship anything over here, right? It doesn't have to be a critical section, in a sense. But we're going to limit ourselves to critical sections over here, with the implicit assumption that critical sections are bottlenecks in the code. In the later work, we will say that, okay, not all critical sections are bottlenecks, because some critical sections are contended, some critical sections are not contended, right? If there's no one waiting for a critical section, it shouldn't be a bottleneck, right? It could become a bottleneck later in the future, But here in this work, we're going to assume that all critical sections are bottlenecks, so all critical sections get executed on this core. Okay, so we add this queue of critical section requests, execution requests, called critical section request buffer. And let's assume that a small core encounters a critical section call. And this is designated with a special instruction, CS call, that's added to the instruction set architecture. And that gets communicated. And P2 recognizes that it's a critical section. So P2 sends a critical section call request to this critical section request buffer in the server, which is the large core. And the large core essentially executes the critical section when it becomes the oldest critical section over here. So this is a FIFO queue, first in, first out queue. We're going to change that in the next work. And it executes the critical section. Hopefully it executes it much faster than P2 would execute it. That's the goal. And when it's done, it sends a critical section done signal, and P2 now can continue. Sounds good, right? And they share memory, so whatever results that this core writes to memory, P2 is able to capture it. Of course, we're going to optimize this in a little bit. Does that make sense? Now, this is a general bottleneck acceleration model. As I said, there's nothing special about critical sections. You can say any piece of code. Basically, you can replace the CS call with bottleneck call, let's say. And that bottleneck call gets executed in P1. That's the idea. It's a very generalized bottleneck acceleration model in that sense. Okay, so let's go into a little bit more detail over here. So this is what you normally do in small cores. If you all had small cores, or if you all had large cores, this is what you would do. You basically compute some result, and then let's assume that you want to update this result using a critical section. You have a lock, you take the lock, you execute the critical section code, and you unlock it. Let's assume that you do something else with the result later on. Now, with the accelerated critical section model, this doesn't get executed in the small core. What the small core does is it computes the private value, the value over here, which is A over here, or the data over here, basically, let's say. Now it pushes that on the stack. So it's going to communicate with the large core through the stack. It pushes the input parameter of the function of the critical section on the stack. And it basically executes a critical section call with the lock X and with the target program counter, which starts from this function, essentially. And that critical section call gets translated into an interconnect request that is sent as a request to the large core. Basically, you send multiple things. You send first the lock, because you still need to obey the locking semantics. You don't want to change the program, basically. And then the target program counter, that's target PC, stack pointer, so that you can figure out where your input operands, input parameters are, and the core ID that's generating this request. And that's received by the large core, and large core enqueues it in the critical section request buffer. And it waits in the critical section request buffer until the large core is available to execute another critical section, because it may be executing a previous critical section request from someone else, or from the same core, potentially, right? If you're doing out-of-order execution, for example. Okay. And then when the large core is ready to execute, it's when this becomes the oldest critical section in the large core essentially starts execution from the target program counter. And you modify the code such that first you acquire the lock over here, similar to here. You pop the result from the stack, pop A from the stack, that's the input parameter to the function. You execute this function over here, and you push the result on the stack so that small core can get it and later use it. You release the lock, and then execute a critical section return instruction, which essentially sends a response on the interconnect back to the small core saying, I'm done with the critical section that you requested. And small core at that point pops the result from the stack and prints the result. Does that make sense? It's simple model-based. It's stack-based communication between the two cores. Because they're shared memory across the cores, we use the stack. Of course, this is not the only way of doing it. You could communicate through the registers if you share registers across the cores, right? Yes? So, yes, basically, that's a very good point. If the critical section is really short, this will have a lot of overhead potentially, right? Actually, let me qualify it. If the critical section is very short and it's not contended, then this will have overhead. If the critical section is short and if it is contended, then this may still benefit. Because all of the contended critical sections will execute in the same place, and you won't move the shared data and you won't move the shared locks. They will all execute in the big core. So there's another benefit, not just the acceleration of the critical section, but shared data and shared locks stay in the same core. Yes?
I guess if the critical section is very short, there's not much benefit to accelerating it
So it's a very similar question. That's true. The acceleration part may not be that beneficial, but if the shared data and shared locks are ping-ponging a lot across different cores, now you're keeping them in the same core. So you could get benefit from that. So there are other benefits from this, actually, which is nice, I think. If you're executing, if you're keeping shared data and shared locks in one place, essentially we're trying to ship the computation to the shared data in this case. You can think of it that way also. But yes, I think you can clearly optimize this. This paper doesn't do that, but you can clearly have a model saying, am I going to benefit from executing this critical section? And we're going to talk about a work that does that, I guess, 4 years later after this. So you need to basically understand the utility of accelerating a critical section. What is the marginal utility that you get? Okay, these are very good points. So you can clearly optimize it. And also, there's also another point, right, which I will foreshadow. This large core, you ship it to the large core, and the large core may not actually accelerate it, right? Because large core, the characteristics of the critical section, the dependencies are such that you're not going to get much benefit from the large core, potentially. That could also happen. And this work doesn't take that into account also. Because, let me give you an example. If all of your instructions are dependent on each other in the critical section, there is no instruction level parallelism, that large core may not provide you any benefit, right? You might as well execute this completely dependent code in a very simple in-order core, right? Yes?
So if the threads, if you have multiple threads, and before the go to the critical section, you have data dependency. So you something, then use it to compute something in the critical section. Then if you have 20 cores, for example, 20 cores, 20 CPU cores in one out of order, then you need to do a big pointing in the cache. Validate all the data in the cores, in single cores. Transfer it all to the large core, and then probably back forth, right?
This is the private data that you input to the function, right?
Yes.
Yeah, we'll talk about that, yes. I think that's an easier problem than channeling shared data. But yes, there is additional overhead, which is really pushing this input data, right? You compute some input data A, and you need to ship that now over there. Even though shared data and locks stay in this core, the private data that's computed by the small cores need to go into the large core.
I mean, this can be like a huge amount of data, right?
That's true. Basically, it depends on the characteristics of the code, clearly. Yeah. So you can clearly optimize this based on the characteristics of the code. That's why you will not get the best performance out of this, but you will improve performance with this mechanism. But you can always optimize it. Okay. Okay, so clearly this has a lot of potential benefit, as we will see, but this has some issues also, like we've discussed. It has also some other issue, which is actually very serious, I think, which is called false serialization. Basically, you have a single large core, and you're shipping all of the critical sections over there, right? What if one core is executing a critical section A, another core is executing a critical section B? Meaning these are different critical sections. They're not touching the same shared data. They're completely independent, basically. If you had executed these in the small cores, you would execute them in parallel. Right? Clearly, you would parallelize these because they have nothing to do with each other. But because we're shipping all of the critical sections to a single core, large core, now they become serialized. And the large core is able to execute only one critical section at a time. This is false serialization. These do not need to be serialized, right? So what we do in this work, this may or may not be the best way of doing it. I believe actually there needs to be more work that needs to be done to understand this. But basically, let's assume that this critical section A, this critical section B, they have nothing to do with each other. And you have a critical section call request to A. That's good. What we do is we keep track of how much false serialization you get because some other critical section is being executed before you. Basically, how many times are you serialized in a false manner? Right? That's the idea. For A, in this case, you're not serialized because you're executing it. Now you get another critical section called A over here. This is fine. These are supposed to be serialized, right? You cannot execute two critical sections called A because they're the same critical section. So you reduce the false serialization counter. Now you get a critical section called B. Now this poor critical section cannot execute until these two critical section called A's are executed. Now that's not good. Because if this stayed in its core, it would have executed right away. Right? That's the idea over here. So you increment the false serialization counter for that one. And basically, the idea in this paper is if the false serialization counter is too high, you don't ship the critical section to the large core. Basically, we want to limit the false serialization. That's the idea, which makes sense hopefully. But of course, there could be better ways of handling this clearly, right? But this is always a problem when you have a single server and when you're shipping your functions to that single server as opposed to executing your functions locally. You may get a bottleneck in the single server that is executing. So what is the solution? One solution is this. One other solution is multi-threading the server, right? Meaning the server itself can execute critical section call A and B in parallel. If it is hardware multi-threaded, it could do that clearly. But now, of course, there's a downside, which is your benefits of accelerating the critical section is becoming lower because now you're contending for resources in the large core between two different critical sections. The other solution is, of course, having two servers, which is two large cores. Now then, that's good. Critical sections are accelerated, assuming that large cores are effective at accelerating critical sections. But now your area overhead dedicated for large cores grows. And we discussed that area overhead last time. We'll discuss it a little bit more right now. Okay, does that make sense? Right. So these are issues that you run into distributed systems programming. If you've done distributed systems programming, you would run into these issues. Should I ship this function to a server? Should I execute it locally? If you have that choice, anytime, you will always run into this sort of issues. Okay, so let's talk about the pluses and minuses. There are performance trade-offs associated with it, clearly. Clearly, hopefully, you get faster critical section execution, but that's not guaranteed, as we discussed, because the core is really not specialized completely for critical section execution. The other benefit, as we also discussed, shared locks stay in one place. You get better lock locality. One place is the large caches of the large core. So that's one other benefit of a large core. You get large caches to keep the shared locks. Shared data also stays in large cores, large caches. You get better shared data locality, less ping-ponging. Essentially, you reduce the probability of ping-ponging. Ping-ponging, we didn't really formally define ping-ponging. But essentially, if you have a bunch of processors, and they all need to execute the critical section at any given point in time, each of them has to acquire the lock at any given point in time, and each of them has to acquire the shared access to shared data, which means that at some point, processor 1 is executing the critical section. It has the lock in its cache. It has the shared data. And when some other core needs to execute the critical section, it needs to acquire the lock, which means that it needs to get the lock variable from the other core's cache into its cache, and also the shared data that's updated from another core's cache to its cache. So the shared data and locks need to move between caches. So they need to ping-pong between caches, travel between the caches. This is only if you're updating the data, of course, right? And when you're acquiring the lock, usually you're writing to a memory location, which means that you're updating the location. If it were read-only sharing, if everybody were reading the same shared data, that's no problem, right? Then you can have multiple copies of the data replicate in the caches, and there's no coherence problem. But if somebody's updating, then you will run into the ping-ponging problem, like this one. And whenever you have a lot of contention, this ping-ponging becomes a huge overhead, because one processor acquires the lock, now the other processor needs to acquire it, now the other processor needs to acquire it, and they travel around the chip, and sometimes outside the chip also, depending on how big your multiprocessor system is. Now if you localize everything in a single core, locks and shared data don't travel, right? They stay in the same place. It's actually very powerful. You get good locality. And the paper shows that even though you may not be able to accelerate the critical section, sometimes your benefit comes from just improving the shared data and lock locality. Okay, so these are some pluses. There are minuses, of course. Clearly, as we discussed, in this case, we dedicate the large core for critical sections. You don't have to do that, but dedicating is a good idea because you never know when you need to execute a critical section, right? If you're executing something else, and when someone ships you a critical section, then you have a context switch overhead. You don't necessarily want to do that. So we dedicate it here so that only critical sections execute over here, and the serial parts. Clearly, this leads to some reduced parallel throughput because you're not using this large core except for critical sections. So if you have a program that has no critical sections, this wastes some of the resources. Of course, you can be smart and detect that, but we're not talking about that now. So clearly, there's some control transfer overhead. Critical section call and critical section done signals require some time to transfer, but that could be overlapped with execution, especially if your especially if your core is busy executing critical sections. You can overlap these overheads. The other overhead that we discussed that one of your colleagues mentioned is the thread private data now needs to be transferred to the large core. Right? That's the A that we showed over here. Oh, I don't want to go back because there's an animation. But basically, the data that's generated by a small core and that needs to be input to the critical section now needs to be transferred to the large core. So even though you get better shared data locality and lock locality, you get worse private data locality. And if this private data is huge, as you mentioned, there's a problem. Because everybody needs to transfer a lot of private data into the large core, and now you cause a lot of communication. Then the question is, which one's bigger? Is your private data bigger, or is your shared data bigger? And there's a lot of interesting analysis in the paper. You can look at that. But let's take a look at the performance trade-off. So these actually correspond to each other somehow. Basically, in the parallel part of the code, we have fewer parallel threads because we dedicate the core for execution for critical section. But we get some benefit out of that also. We accelerate the critical sections now. So the question is, which one is better? So it turns out accelerating critical sections in the applications we examine offsets the loss in throughput in the parallel part. And actually, this is a reasonable trade-off. As we discussed this yesterday, as the number of total cores or total chip area increases, the fractional loss in parallel performance decreases. So let's assume that you have a chip area that's equivalent to 16 small cores. You dedicate 4 cores to critical section execution. You lose 25% throughput in the parallel parts because 4 out of 16 is gone. Right? But if you have a chip area that's 64 small cores, you dedicate only 4 of them to execute critical section, you lose 1/16 throughput, which is much smaller than 25%. So as the chip area increases and as the large core sizes don't grow as fast, you lose less throughput in the parallel part. And also, as the number of cores or chip area increases, there's more contention for critical sections once you keep parallelizing your program. And that makes acceleration more beneficial in the end. So this is not a bad trade-off, I think. And also, you can fix the trade-off somehow by using the large core for other execution, like parallel execution. But we're not going to talk about that over here. This is the other trade-off. You get some overhead for shipping the critical sections, say CS call, CS done signals, but you also get better lock locality. You can think of it that way. Lock locality corresponds to CS call. It's essentially an overhead for doing the locking, in a sense, right? CS done is also another signal that you introduce to release the lock, in a sense. And it turns out ACS, accelerated critical sections, avoids ping-ponging of locks among caches by keeping them at the large core, and we discussed that. So this actually is a good trade-off also. Now this is the last one. You get more cache misses for private data versus fewer misses for shared data, because shared data stays in large cores, large caches. Private data needs to be communicated. Now the question is, which one is larger? Or which one is an easier or harder problem? We'll actually talk about this later on. Any guesses? Anyone who has done parallel programming? Do you normally have a lot of shared data? Do you normally touch a lot of shared data in a critical section? Or do you touch a lot of private data in a critical section? You say shared data. Why?
Because otherwise it wouldn't be critical.
Okay, I like the mentality there because in that case, you're really trying to optimize a critical part, right? You really are updating a big shared data structure, and you maybe have a small update to do on that big shared data structure. That's the normal critical section mentality in a sense. But it turns out normal programs are not always like that. So there are some cases where you're updating a single shared variable, and you're really aggregating many things. But of course, I think I would argue in that case that you need to do a better job optimizing your critical sections, but most programmers don't do that better job. So they actually put a lot of private data into the critical section, and a lot of that work can be done in separate critical sections, actually separately, as opposed to having a single large critical section. Okay, so let's take a look at one example. This is going to basically an example that validates your mentality. So basically, we have a priority heap, and we want to insert some. So this is actually, heaps are used in a lot of dynamic tasking mechanisms. Remember, we talked about dynamic tasking. You actually have a shared data structure, and threads actually take out problems from that data structure, and they basically work on that problem, and they're done with the problem, and then they go back to the shared data structure, and they take out new tasks. So this is one example where you could actually generate a dynamic tasking heap. So basically, you insert some new subproblems, So in this case, the shared data is huge. There's a lot of problems initially, and somebody generates new problems. And if you want to update the shared data structure, a lot of threads may be touching it at a given time. It's really a critical section. But the input data is very small. Basically, you want to insert one node to a data structure that may have 1 million nodes, right? Clearly, in this case, the shared data is huge, and the private data that's generated by one thread to update the shared data structure is small. So the number of things that you touch in the shared data is a lot compared to the size of the private data. So this is one example that works like I would normally expect. But it doesn't always work this way. Sometimes you get this greens from everywhere, but that's because you may not really optimize your program really well. But again, you cannot fault the programmer for that, right? The inclination is that you can say, okay, the programmer did a bad job. Yes, they did a bad job, no question about that. But maybe they were busy with other stuff, right? That's why this is important. And this, I think this debate will continue forever. You can always fault the programmer saying they didn't do good enough of a job. And that will always be true. But there are limited resources, and they may have other priorities. Okay, so in this case, shared data is larger than private data. So basically, cache misses reduce if shared data is larger than private data. And the paper has some analysis. That's not always the case in all of the programs, because some of these programs are not completely optimized, and But I will also say that this problem can be solved. It's usually easier to predict which private data that you're going to generate earlier than which shared data that you're going to touch. And we will see that later on. We will get back to this. And we will use this observation to actually identify what is private data and ship it to the large core before the large core needs it. So you can think of this as a prefetching mechanism. Basically, you're identifying what's the private data and shipping it to the large core earlier than the large core needs it. It's a push mechanism, basically. You're pushing the private data earlier to the large core. It's very hard to do that with shared data, because once you're in the critical section, you have this 1 million entry heap. It's very difficult to figure out exactly what you're going to touch, because it's very dependent on the data itself. Whereas private data, you know what instruction is kind of going to generate that data, right? Actually, you can do dependency analysis in the code. If you go back over here, clearly you can do dependency analysis in the code that says, okay, this is going to generate some data that's going to be input in the critical section, so why don't I actually do it earlier and push this data to the large core earlier? Right? You could do that. So a smart compiler is able to do that, I think. But we're going to look at a hardware mechanism to do that, a hardware-software cooperative mechanism to do that. Okay, basically we're going to talk about this later on, data marshalling. Okay, so let's take a look at performance results. Any questions so far? This all makes sense to everyone? It's cool. Basically, we're building a server inside a chip. You have a server for dedicated execution of critical sections. But I think in the bigger scheme, you really want servers that can execute different things. And this leads to massive heterogeneity in the end. You have this function call. Okay, I have the server that's specialized for it. Let me ship it there. Yes? Yeah. No, unfortunately not. Not yet, as far as I know. As far as I know, not yet. But people actually looked at implementing it, and yeah. I don't know, sometimes good ideas get implemented much later than expected. Okay, by the way, this paper was, I guess it's the same as the phase change memory paper, which is also 10 years ago. That got implemented this year. Yeah, okay. Okay, so let's take a look at, basically we're going to compare the performance of these three different things. Basically symmetric small cores, asymmetric multi-core, where large core executes large core executes only the serial parts of a program, and accelerated critical sections where the large core executes as we discussed, both the serial part and the critical sections. And again, we're not going to discriminate between critical sections. All critical sections go there. That's not necessarily the right thing to do, as we will see later on. And we examine a bunch of critical section intensive applications, as you can see, and there are many of them in the world. And it's simulated because it's very difficult to actually build this right now in real systems. Although with open hardware, I think these ideas can be examined a lot better right now with the RISC-V hardware that we have. And if people are interested, I would recommend looking into these ideas that way going forward. And you can read the paper for more detail and simulation methodology. These are not the easiest things to simulate, by the way, I will say that. these simulators that, so if the simulators that we've previously been discussing, multi-programmed applications, are relatively easy to build. Multi-threaded simulators are a lot harder to build because you really need to be very careful in terms of how you handle the locks. Because you're not, in the end, you're prone to everything that we've discussed. It's very similar to multi-threaded programming, but now you're simulating multi-threaded programs. Okay, and also you need to be careful in terms of how you do the comparisons over here. So this is one comparison result. Basically, here we have an equal area comparison. Basically, we have equal area across different things over here. I think some number of core area. I don't remember what it was. Basically, it's over here. Yeah, 1 large and 28 small cores. Basically, the equivalent of 32 small cores. But, yeah, it's over here, actually. Chip area is 32 small cores. For symmetric multi-core, you have 32 small core. ACMP, you have 1 large and 28 small cores. But you don't want to run everything at 32 threads, because that's not the best point for every program. Basically, what we do is we pick the number of threads to execute as the number of threads that lead to the best performance on a given system for a given application. For example, for puzzle, for example, it may be only 3 threads that gives the highest performance to you, as we will see. Actually, let me go to the next one over here. Yeah, this is an example. Let me pick puzzle. So puzzle is here, right? So these are, the black one is a CMP. It's actually green. Red one is ACMP, which is asymmetric multicore. And accelerated critical sections is this one. So you can see that puzzle's best point, the most scalable point in an ACMP and SCMP is about 8 threads. So we pick the 8 threads as a comparison point, and we compare it to the best point over here in ACS, accelerated critical sections. If you do the comparison at 32 threads equal, that's not a good comparison, because 32 threads is not the best point to run this application with, right? Although you could ask the question, how do you know that? Which is also actually a very interesting question, because when you build a multi-core system, you build 32 threads, you expect people to run with 32 threads. Do programmers figure out what is the real number of threads they should run the program with, right? They may not have enough effort. So even understanding how many threads you should use to run a program is very important, and it's not done very well today. And you can see it makes a huge difference. For example, PageMine. I'll pick this example. Basically, if you run it with 8 threads, you get 3x speed up, let's say, around 3x. If you run it with 32 threads, you get a slowdown compared to the baseline single-threaded version. Why? Because 32 threads, there's just too much contention in these workloads. But if with 8 threads, you get a reasonable speed up, 3x. Not bad, right? It's respectable, actually, if you want to get 3x. It's clearly not the linear speed up, but it's respectable. So in these cases, you've got to be careful. In fact, I think choosing the number of threads dynamically to run an application with is still an open problem. There's a paper about it called feedback-driven threading. It does some optimization. I will briefly talk about that later on, but there could be more work in that area. Because as a programmer, actually, I will ask you, how many of you have done multi-thread programming? Okay. How do you choose the number of threads you run an application with? The most. Basically, this gives you a reason not to do that. Of course, if you know your program, if you know that it keeps scaling, no problem, right? But not all programs are that way. For example, this one is okay. This is a traveling salesman problem. And you can see that it's okay, I guess, right? SCMP, symmetric multicore. Yeah, the most is the right answer over there. But the most is not the right answer for many workloads. Does anyone want to do something better than the most? Yeah, that's what I would expect also, actually. Real programmers do that in the end. They pick some value, maybe the most, maybe the middle, maybe whatever. But they cannot really optimize, search the entire space in the end. Because also the spaces depend on the input set. You may see this behavior with some input set. This behavior might change with some other input set, like we discussed with sort yesterday, right? Okay, basically this comparison, what it does is it selects the best number of threads for a given system and for a given application, and compares the best point for each. And if you do that, you will see that there are 2 kinds of applications. One is the applications that are over here, let me go back, that have coarse grain locks. These are applications that are not very optimized by the programmer. And you can see that, so let's look at exerting sequential kernels. Basically, you execute the serial part of the program in the large core. This depends on the serial part of the program, and there are some cases where the serial part is very large, as you can see in quicksort over here. So you get about 45% by going from symmetric multicore to asymmetric multicore, where you use the large core just for accelerating serial parts. On top of this, if you accelerate critical sections, like we've discussed, you get a lot more speed up, right, for these programs. So the blue bar is accelerating critical sections compared to the light blue or turquoise bar. And you can see that there's a significant speed up. This is 2.7x. This is 1.1x, let's say. So you can see the benefit of this if the programs are not very optimized. If the programs are more optimized, you can see you'll see less or more modest benefits. You can see that we call these fine-grained locks. So people try to optimize them more. Maybe they could do even better. As you can see, we still get significant speed up, around 20%, for example, in these online transaction processing workloads. Essentially, you get significant performance benefit from accelerating critical sections. There are some cases you lose performance, not because accelerating critical sections, but you put the serial part into the large core. And this is because you lose some parallel throughput. These programs are more optimized, and you lose parallel throughput, and you cannot recover that by accelerating the serial part. So you could, of course, do better if you actually optimize the system. So here you don't gain much performance, clearly. Yes?
How do we determine which one is critical section?
So in this case, the critical section is marked by the programmer. Make sense? So you basically insert a critical section call instruction at the beginning of the critical section.
So it's not dynamically by the hardware?
No. So as I mentioned earlier, I think yesterday, I said that you could do this purely in hardware, but then you need to discover the critical sections, which may not be easy. And that's actually one of the reasons you had the question, why has it not been implemented? I think part of the reason it's not been implemented is you need to discover these critical sections nicely. Say it again? That's true, but they get translated into very different structures later on, loads and stores, and they do not always get communicated with the right instructions, with the right semantic information, basically. So in the libraries, you do use locks, yes, but they get converted into loads and stores.
They could get converted.
Exactly, but they don't exist yet. So you need to change the instruction set architecture. So everything is a barrier to adoption, basically. I agree it should be implemented. Yes?
Would it be possible to explain what puzzle and web cache do?
Oh, I see. Well, I don't really remember right now at this point, but so puzzle, I think, it's a game that solves a puzzle game, and the code is online. So if you look at the paper, I'm going to assign this paper as homework now, since you're interested. No, I'm just kidding. I was going to assign it anyway. But basically, it's a game that solves a puzzle, but I don't remember exactly what the game was. Web cache is essentially a web cache. It's really a cache where you do a lot of updates into the cache. It's really a software cache, basically. IP lookup is an IP lookup table, for example, where it's a router IP lookup table. But all of these are actually, they have their source code somewhere online. TSP is from the olden benchmarks with traveling salesman problem, which you may know of. And some of these are benchmarks that are, like SpecJBB is a Java benchmark, the Java server benchmark that people use. I don't know if they still use it, but at the time they used it. Okay, it's fascinating, isn't it? So I think this is a very good example of programmer-microarchitect trade-off also. Like, programmer doesn't optimize their code, microarchitecture helps, or architecture helps a lot. Okay, so overall, on average, you get significant performance benefit. Okay, let's take a look at this. So clearly, these applications are selected such that they're somewhat intensive in critical sections, right? If your application is 100% parallelizable, this will not give you benefit. No question about that, right? That's why we're not looking at those applications over here. That's why you're seeing scalability curves that look like this. If it's 100% parallelizable, these parts should be around 32, right? But these are the hardware applications. 100% parallelizable applications are not the hardware applications, clearly. These are the hard applications. Somebody had difficulty parallelizing them. Okay, so if you look at equal area comparisons, I'm not going to say that. Basically, these are the scalability curves. This is the chip area that you dedicate, and what is the performance you get. Essentially, ideally, you would like things that look like this, right? Puzzle, basically. It keeps scaling. And it keeps scaling with only the accelerated critical sections over here. It's not ideal because it goes up to 6, as you can see, as you keep adding up to 32 cores. But overall, what happens is scalability improves. Scalability is the maximum number of threads that give you the highest performance. You shift the scalability point from here to here. And that's true for other applications like here. And that's true for actually 7 of the 12 applications, I think. Their scalability point is shifted to the right. For the remaining applications, I think they remain the same even though performance improves. So here it's the same, I think. Okay, so this is the summary, basically. I think I'm not going to go through this again, but we've already discussed this. This is the idea of accelerating critical sections. So we want to now generalize the idea. Can we... we're going to still maintain the scope of parallel applications, but can we accelerate all bottlenecks or critical paths in a parallel application by executing them on a powerful core? But before we go into that, this is the paper, and how do we generalize it? So I'm going to talk about this one. Any questions so far? It's good that you had a lot of questions. I guess people are having a lot of pain with multi-threaded applications. So think about writing a multi-threaded simulator. I'm not going to make you do that in the last lab, but that's also a pain. Okay. Although it's a pain, even though you would actually think that multi-threading processor simulator is a great thing because there's a lot going on in parallel, right, in a processor. Multi-threading actually should work, but there's a lot of synchronization that also needs to happen across different parts of a processor. And that's where the bottlenecks come in when you do a multi-threaded processor, multi-threaded simulator for a processor. Okay, now we're going to generalize the idea to different bottlenecks in multi-threaded applications. And so what is the generalization? Basically, now we're going to think about a bottleneck as any code segment for which the threads contend. In other words, weight. So we're not only going to generalize the idea, we're also going to refine the idea because we actually want to not accelerate things that the threads are not contending. So we already talked about examples, serial portions. Only one thread exists. Clearly, it has to be on the critical path. Critical sections, they ensure mutual exclusion. They're likely to be on the critical path if they're contended. Barriers to ensure that all threads reach a point before continuing. The latest thread arriving is on the critical path. And pipeline stages, different stages of a loop iteration may execute on different threads. And slow stage makes other stages wait. And it is likely on the critical path in that case. And you've already seen all of these before. So let me give you another observation. Basically, it turns out these limiting bottlenecks change over time. They're not static. You cannot look at a piece of code section and say, okay, this is the bottleneck. It may look like the bottleneck, but if it's not contended, it changes over time. I'll give you a very cooked up example. You can cook up any kind of example, actually, and you will find out that these cooked up examples exist in real code. So this is one cooked up example. We have 2 linked lists. A is full, B is empty. And we actually have a thread that's going to do this. And we're going to have many threads that's going to execute the same loop. What are they going to do? Basically, each of them is going to take one item from the full linked list and do something on it and append it to the empty linked list. That's the idea. Basically, this is lock A. You remove an item from list A, and then do something on it, and then insert the item into list B until list A is empty. And every thread is going to do that. Clearly, there are 2 critical sections over here, right? And you can identify what's the private data, what's the shared data clearly this way, right? Here, the shared data is the linked list A. Private data output becomes X. Here, the shared data is linked list B. Initially, it's empty. So initially, shared data is small. Private data is always one item that you're going to insert. So you can actually do a lot of analyses in this cooked up example also. So this is the execution of this code with 32 threads. 32 is a decent number. And this is what happens, basically. And this is what you would expect, basically. So this is the time in terms of millions of cycles, and this is contention for the 2 different critical sections. Contention is measured as the number of threads that are waiting for that critical section. Initially, the blue critical section is very contended. That's lock A, because the linked list is huge, right? It's big, and everybody's trying to remove stuff from there. And over time, this list becomes smaller and smaller, and this part becomes more and more contended. Clearly, bottlenecks kind of shift. Right? Here, lock A is the limiter. Here, lock B is the limiter, and in between, both may be limiters, right? That's the idea, basically. So the idea is somehow adapting to this. Here, you would like to accelerate this one, because there are some threads over here, but maybe this is not very content because very, very small critical section like we discussed, right? But over time, this grows a lot, and it becomes a bottleneck. Okay, so you will really like to adapt to these bottlenecks dynamically. You want to accelerate this one, but not this one over here. Maybe you want to do half and half over here. And clearly, you don't want to accelerate the blue one over here, and you want to accelerate the red one over here. And you can say this is a cooked up example. Actually, life is a lot more complicated. This is an example, very short time period from MySQL running some queries with 16 threads. And these are two different locks, opening the database tables, or locking the log. And you can see that the bottlenecks keep shifting, right? Here, for example, opening the database table seems to be a big bottleneck because the number of threads waiting for that lock is very high. The maximum is 16, as you can see. And then the bottleneck shifts. Sometimes the logging becomes a bottleneck, and sometimes the blue part becomes a bottleneck. So you really want to adapt to this dynamically. Okay. So basically, the idea is bottleneck identification and scheduling. And it's really a refinement and generalization of what we just discussed. And the key insight is we really want to identify thread weighting, because thread weighting reduces parallelism and is likely to reduce performance. If you're waiting, you're basically wasting some execution cycles. And code that's causing the most thread weighting at a given time is likely the critical path. Determining the critical path of an application is actually very difficult. It's an NP complete problem, it turns out. You can actually do studies on it also. Especially dynamically. Like dynamically while you're executing, how do you determine what's your critical path? But this is a heuristic to guess what your likely critical path is. And we're going to try to guess that by finding out which code is causing the most thread weighting. And the key idea is basically simple once you have this heuristic optimization in mind. You dynamically identify the bottlenecks that cause the most thread weighting. Somehow you need to be able to do that. And accelerate them using powerful cores and ACMP. But again, you can use other techniques as we discussed, right? You can prioritize them. So the question is, how do you do this? This is, again, a hardware-software cooperative mechanism. Again, you can imagine purely hardware versions of it. It becomes complex, in my opinion. It's a lot easier if somebody provides you the high-level semantic information about what the code looks like. So basically, compiler, library, and hopefully not the programmer, does this. They basically annotate which code may potentially be a bottleneck, and they also implement weighting for bottlenecks. I'm going to show you what exactly that is. Basically, if some code waits for a bottleneck, you increment some counters. So you need some support for it. And then you basically generate a binary containing these instructions that do these annotations. And while the hardware is executing, it basically sees a potential bottleneck. It basically records how many cycles that this potential bottleneck has caused other threads to wait. This is called thread waiting cycles. And it basically records for each possible bottleneck how much waiting it has caused to other threads. And at some point, it figures out, oh, there are some bottlenecks that lead to a lot of thread waiting. As a result, it accelerates them. That's the idea. Hopefully, it's a very simple idea. Okay, so then the question is, how do we actually do this annotation, right? Basically, we want to be general. I mean, the general thing is you can annotate any code as a bottleneck. Bottleneck start, bottleneck end, right? Potential bottleneck. And then give an ID to that. And then the hardware can actually start measuring how much waiting that it causes. That's the idea, basically. Basically, if you look at a lock, it looks like this. While you cannot acquire the lock, you wait. And then you figure out that you can acquire the lock because nobody else is waiting for the lock. You acquire the lock, this is a critical section, and then you release the lock. That's a common pattern for a lock. It doesn't always look as nice as this. That's why it's not always easy to determine what's a lock and what's not a lock if you don't use libraries, right? But people use libraries with locks. Assuming that you use libraries, this identification is easy. What we're going to do is we take this function, we're going to outline it. If you use libraries, it's already a function, actually. And then we're going to encapsulate it with a bottleneck call. And this bottleneck call says it will assign a bottleneck ID to this and a target PC. So bottleneck call means that you're going to potentially start a bottleneck with a bottleneck ID at target PC. And then you keep executing it. And you do a bottleneck return at the end, which means that the code is done. So that's how you delineate the bottleneck, right? By assigning a bottleneck ID, and that's the bottleneck code over here, and you delineate with call and return. So it's a function call and functional return, but it's a very specialized function call and functional return. It could be a bottleneck because we're going to do something with this information soon in the hardware. So the next question is, of course, you are in this bottleneck. Here you're really waiting for someone else to get out of this bottleneck code, right? You're basically waiting for this particular lock to be free. So we want to actually keep track of that. How many cycles do I wait in this loop? This is a spin loop. You're basically spinning and waiting for the lock. So basically we're going to add another instruction that says bottleneck wait. We're waiting for this bottleneck ID, which is this thing itself, and we're going to do that by watching an address. Basically somebody is going to write to that address and say the lock is done, so now I can go back and acquire the lock. That's the idea. So now this instruction can help us to increment a counter associated with this bottleneck ID. Saying every time we execute this instruction, we know that we're waiting for that bottleneck, right? Because somebody else is there. Because I couldn't acquire the lock. That's the idea. So it's used to keep track of waiting cycles. And these are used to enable acceleration, as we will see. So this is the locks. So of course we want to generalize it. We want to actually do it for barriers. So this is an example for the barriers. Again, I will briefly talk about it, not go into a lot of detail. But basically, normally with the barriers, you have a parallel part. There's code that you execute that's running for the barrier. And once you reach the end of the barrier, you're done with the bottleneck, right? Somebody calls us, basically. This is how you actually do it. You enter the barrier code. While not all threads are in the barrier, you wait. Otherwise, you exit barrier code. So basically, this is how you do it. You execute the parallel part. Once you're done, you basically synchronize. You do barrier synchronization. You enter the barrier code, which is the synchronization part. And in this case, you're assuming that you're waiting for all of the other threads. And there's some counter over here that's updated, shared counter clearly. While not all threads are in the barrier, you keep waiting. Right? Once all threads are in the barrier, you're done, and you can execute whatever comes next. Make sense? You're done with barrier synchronization. So this is how you take into account the bottlenecks in terms of barriers. So barriers are a bit special. You can read the paper for more detail, because you need to really predict which thread is the bottleneck. It's a little bit different from the locks. But you can still identify which thread is lagging behind this way. Okay. So this is another example, which is pipeline stages, which we discussed earlier. You have you basically made your program staged, and you have stage A, stage B, stage C, and different threads execute each stage, right? In this case, this is the stage. You do the work. Essentially, that's the parallel part or pipeline part. But of course, to be able to do the work, you need to be able to get an input from the previous stage, and this is how you do that. Basically, there's a queue before you. If the queue is not empty, you dequeue the work and then do the work, and then you produce some output. And if the output queue is not full, you enqueue the work, and then you're done. But you run into problems if the previous queue is empty, right? If your input queue is empty, you need to wait for the previous stage to generate some input for you, which means that the previous stage is actually a bottleneck for you, right? You're waiting for the previous BID, the previous stage. You're fine, you're executing okay, your input queue is empty, which means that somebody else is not catching up with your speed. On the other end, if you have a full queue at the end, you may have the same problem on the other side, right? Basically, if you have a full queue, you're done with the work, you cannot enqueue it, which means that you need to wait for the next stage, which means that the next stage is the one that's causing the bottleneck for you. So basically, you need to insert these instructions in the right places, but these can be done methodically if you have a library. And of course, you need to have a bottleneck call and bottleneck return also, because this is really the part that you need to accelerate when you go into it. Okay, and you can actually extend this to any synchronization primitive. This paper talks about 3 synchronization primitives that are heavily used, but you can actually extend it to condition variables, semaphores, etc. Those are a little bit more overhead because those are actually faster synchronization primitives than these. Barrier synchronization or stages can be very big, actually. Okay, does that make sense? Any questions? Now you can see that this is actually harder to identify purely in hardware. That's why I like this semantic information to be communicated to the hardware nicely with some sort of interface. Okay, so now we have somebody that did this marking. If the programmer programmed in libraries, code is nice. All of the synchronization code is done through a library, and the compiler can analyze that code, analyze that library, and can generate this code nicely. If the programmer didn't do programming with libraries, then they need to insert this code clearly. Right? Or you need to have a software path that identify what's the synchronization path. The beauty of libraries is you can easily identify, okay, this is my synchronization primitive. If the programmer played a lot of tricks in their code, and they actually implement the lock using loads and stores and whatever variables that they generated themselves, it's harder to analyze the code clearly because you're really trying to pull semantic information out of the code. Okay, now you have a binary that's containing these instructions. What are we going to do in the hardware? It's easy, I think, at this point because you have all the information that you want, in a sense. So basically, there are two things that you want to do. First of all, you want to identify, now you know what are the bottlenecks. You want to identify what are the limiting bottlenecks, and you want to accelerate. So these are clearly two independent tasks. Acceleration can be accomplished in multiple ways, like you can increase the core frequency and voltage. We will discuss that briefly later on. You can prioritize this bottleneck in shared resources, as we discussed, or you can migrate to faster cores and asymmetric multi-core. This is what we're going to discuss. But you could also increase the core frequency and voltage. This can be done today, actually, and this is also this is done in some systems today. Basically, Turbo Boost, Intel's Turbo Boost mechanism, which was introduced, I guess, 10 years ago now, does this. Right? They basically, if you're running a critical piece of code, if you're running only a single thread, that's one example of it. You boost the frequency and voltage of the core, such that you run this core at a much higher frequency and much higher voltage. Everything else, you're running at much lower frequency and much lower voltage. So you're basically distributing the power or energy per instruction across different cores and accelerating one particular serial part. There's no reason you cannot do both. You cannot combine all of these, of course. These can be combined together also. So let's take a look at how we measure the thread waiting cycles now. So I'm going to give you a pictorial example. You have a large core, you have two small cores, and these are going to execute some bottlenecks. We want to determine thread waiting cycles for each bottleneck. So we're going to add some bottleneck table, which itself could be a hardware bottleneck. No pun intended over here, but you need to be careful, actually, because if it's a centralized structure in a 1,000-core system, that's not good. So the paper has some solutions. We'll see an example of it. So basically, we're going to keep track of how much thread waiting each potential bottleneck ID has been causing while the program is running. So let's assume that small core executes a bottleneck wait instruction. It basically sends a signal to the bottleneck table saying, oh, for bottleneck ID 4500, I'm waiting on it. And initially, the thread waiting cycle is 0. But over time, while the small core is waiting, the thread waiting cycles get incremented. Because small core 1 said, I'm waiting for this bottleneck, keep incrementing the cycles until I tell you I'm not waiting for the bottleneck anymore. So you don't have to increment it clearly every cycle. You can actually do it at a coarse grain. You just need to keep track of when this bottleneck wait has started and when the bottleneck wait has ended. Right? That's the idea. Okay, so you keep incrementing it. At some point, small core 2 also starts waiting for the same bottleneck. Now you have 2 waiters over here. Now you keep incrementing it by 2. And at some point, this is done, and bottleneck table is notified saying that the small core 2 is not waiting for it anymore, so it's going to increment it by 1. So clearly, you can keep track of how many waiting cycles each bottleneck has caused this way, right? It's obvious. And then at some point, nobody's waiting for that bottleneck, so waiter is 0, you're not incrementing that. So this is easy. Of course, there are scalability issues. You need to make sure that this doesn't introduce a lot of traffic on the interconnect, ... Read the paper for more detail. So now the question is, how do you accelerate bottlenecks with the highest thread waiting cycles? Let's take a look at 2 examples. Bottlenecks, 4600 and 4700. You have some thread waiting cycles that are accumulated. Now the small core wants to execute a bottleneck called 4600. Now it has the option, should I execute it here or should I ship it to the large core? Now for that decision-making mechanism, it consults this bottleneck table. It asks the question, I want to execute bottleneck 4600. Tell me where should I execute it. And the bottleneck table checks whether thread waiting cycles is less than some threshold. If the thread waiting cycle is too small, the bottleneck table says, okay, this is not an important bottleneck. It's not limiting anyone, in a sense. It's not as important as something else. So execute it locally. And small core executes it locally, and it's done. Everything else in the bottleneck code happens, basically. Okay. And now it gets the bottleneck called 4700. It does the same thing, asks the question to the bottleneck table. Now, the bottleneck table, it turns out this bottleneck is actually a limiting bottleneck because its thread waiting cycle is very large. Of course, how do you determine the threshold becomes an issue, as always. With any thresholding mechanism, that's a problem. But in this case, it's greater than the threshold, and the bottleneck table says you should execute it remotely and sends a signal saying, small core, please execute remotely. Now the small core needs to send a message or packet to the large core saying, I want to execute this bottleneck remotely. To facilitate the execution, remote execution of a bottleneck, we need some buffer, similar to the critical section request buffer. Now it's a bottleneck scheduling buffer. It's not going to be a FIFO. With critical sections, you can be a FIFO, but here we want to take into account the importance of the bottleneck. And we have a measure of importance, which is thread waiting cycles, right? Basically, we have a scheduling buffer for the bottlenecks right now. And we send the bottleneck ID, program counter, stack pointer, core ID, similar to X-rated critical sections. All of that information needs to go here again. But the large core now prioritizes the bottleneck that has the highest thread waiting cycles. So clearly, this can starve some bottlenecks that will never reach the highest rate. So you need to be careful over here, and the paper discusses some potential deadlock issues. So you need to actually be careful how you design this, but I'm not going to go into the detail. But once this becomes the most critical bottleneck, it gets executed. Once the execution is done, you get a bottleneck return, which sends a signal back to the core that started the bottleneck, and the core now can continue execution. So that's the idea. Basically, it's shipping a function based on the importance or criticality of the function to the large core. Make sense? So now we're generalizing the idea clearly. So of course, you don't want to do all of this communication, because if it's really a bottleneck, you want to make a quick decision, right? You don't want to ask a question to some remote core, should I execute it locally or should I execute it remotely? You're adding critical path latency. What we do over here is we actually have these acceleration index tables that are updated once in a while. What these say is where you should execute a particular bottleneck. And small core, when it gets, these are updated once in a while. Small core, basically, when it gets a bottleneck call to 4700, it quickly checks this table locally, as opposed to going through this huge loop or round trip. It quickly checks this local table, and the local table says, execute this bottleneck on the large core because it's a critical bottleneck. I've determined this is a critical bottleneck, and I broadcast it to everyone. And that happens only when the bottlenecks exceed some thread waiting cycles. Now that gets rid of this handshake, if you will, and then you can accelerate this bottleneck very quickly. Make sense? Of course, this adds more complexity, right? But whenever you need to make a decision, you want to make that decision quickly, and you want that decision to be local. Yes?
But it can change, right?
It can, yeah, exactly. Whenever it changes, it also updates. So there's additional traffic. But hopefully those updates are not on the critical path. Those updates happen once in a while. Okay. And clearly there's provisioning for multiple large cores over here. Actually, in this paper, we look at having multiple large cores to accelerate different bottlenecks. Some bottlenecks you can send here, some bottlenecks you can send to some other large core. If you have enough chip area, you can actually do that. Right? And again, you can customize some cores for barrier execution. You can customize some cores for particular critical section execution. You can customize some cores for different staged execution for pipeline parallel programs. We're not doing any of that here. These are all general purpose cores. I believe if you really want to customize your program for parallel execution, you really need to customize the cores for the type of bottleneck that you're executing. Okay, so these are the mechanisms for BIS. Basically, it's very similar to accelerated critical sections, actually. Determining thread waiting cycles is new. Accelerating bottlenecks is somewhat similar. And we still need to deal with false serialization that exists. There's something called preemptive acceleration that I'm not going to talk about. You can actually look at it. But this is mainly for when you're running towards a barrier, your thread waiting cycles may not have accumulated so much. So you actually preemptively accelerate a barrier. But I'm not going to talk about it. You can read the paper. And there's support for multiple large cores over here. Hardware costs. Actually, hardware cost is not bad. It's really the complexity that matters, actually. If you really want to make it work, you really want to get all of these pieces right. It's similar to fairness via source throttling in a sense. Complexity is the harder part. The hardware cost, if you actually calculate the storage cost, is not that high. And all of this is off the critical path, so you actually don't add anything to the critical path. So even if you have a system that's equivalent to 64 small cores, you get less than 19 kilobytes storage cost. But it's really the complexity that's difficult here. And you still have similar performance trade-offs, right? You get faster bottleneck execution, but fewer parallel threads because these cores are dedicated to bottleneck execution. Very similar trade-off. You get better shared data locality versus worse private data locality. Shared data stays on the large core, that's good, but private data migrates to the large core. But again, we can use data marshalling, which we're going to talk about, which is an orthogonal idea that could be used for many things. And you get the benefit of acceleration, but you get the migration latency, right? And usually migration latency is hidden by waiting. If you actually are identifying the limiting bottlenecks, whenever you migrate code to be executed on the large core, hopefully you're going to wait over there, right? Because there is a bottleneck over there. Because somebody else is also executing that bottleneck. Which means that the migration latency for your private data, or for whatever, the code migration latency, is actually going to be hidden. Actually, migration latency of your private data may be hidden because of that as well. Unless the bottleneck is not contended. So if you're shipping something that's not contended to the large core, you're probably not doing the right thing anyway. Right? You don't want to use the large core for that. So it's not good for energy, but maybe you're not doing something bad. But that causes false serialization. That's one reason not to ship not contended bottlenecks to a large core, because you cause false serialization, right? Okay, let's take a look at the performance results. Again, we're going to look at very similar applications over here. In this case, we added some more barrier-intensive and pipeline parallel applications as well. And you can see that we have some number of cores, and you can see the different types of cores over here. As I mentioned, large cores are heavy out-of-order cores. Small cores are simple in-order cores. You can think of it that way. And we're going to compare to symmetric multi-core, all small cores. Asymmetric multi-core accelerates only serial parts. Accelerated critical sections, which we already saw. Accelerated critical sections do not work for pipeline parallel workloads or barrier-intensive workloads. They work for locks, mainly. And there is also something called feedback-directed pipelining. The idea over here is it's a software mechanism. Dynamically in software, it figures out what are the slowest pipeline stages, because you can easily measure this, right? By adding right instructions that basically tell you how many times, what is the throughput? Basically, what is the throughput of each stage? You can calculate that relatively easily. You can figure out how many portions you're retiring in a given second. And you can actually feed back that information to a software-based runtime system. And the software-based runtime system schedules the lowest throughput or slowest pipeline stages on large cores. You can actually do all of this in software for pipeline parallel programs. You can do everything I said in software, but the migration overheads become large. If you have this information about what's a bottleneck, you can actually ship things to software. Actually, there are works that did this in software, and they may be implemented in real life. So you ask the question, is it implemented in real life? The software versions of this can be implemented in real life, and I know that there are papers. I think it was in ASPLOS 2012, 2013, one paper, that does this exactly in software. You basically form a software bottleneck acceleration core, and software ships the bottlenecks to that core. But of course, the overheads of that are relatively high, and we're going to compare to that, this one over here. So let's take a look at the performance improvements. These are, again, similar methodology. You compare to the best threads, because if you compare to the worst threads, actually performance improvements are even higher. That's the optimal number of threads. The speed up normalized to the ACMP. The blue parts are accelerated critical section and feedback-directed pipelining. And for some workloads, feedback-directed pipelining is not applicable. And for some workloads, accelerated critical section is not applicable. So we really need to combine them. And you can see that in these workloads, there's a large performance gain with bottleneck identification and scheduling. In some cases, more than 40% over here. And this is because limiting bottlenecks actually change over time, and you're basically more careful in terms of what you're accelerating. Whereas accelerated critical section is not very careful, right? It's getting performance. This is actually similar to what you've seen in the earlier results, MySQL. It's getting performance, but it could do a lot better, as you can see, if you're actually more careful in terms of what you're accelerating. Now we have a good heuristic that tells us this is likely a limiter portion, and we accelerate that one. So unfortunately, spec JBB is upset over here. You can see that it doesn't gain a lot. But that's normal, I think. Some workloads will not gain a lot. So these other workloads that are that are barriers, accelerated critical section cannot accelerate, but this work can accelerate because it's more general, as you can see. And overall, you get significant performance improvement. Okay, and it improves the scalability of 4 of the benchmarks compared to the blue things over here, basically the best previous mechanisms. So there's another question: why does this work? It's actually good to do this sort of studies. And this study is not very easy to do because we wanted to really identify what is the critical path of a program and what fraction of the time we're correctly capturing that critical path. That's the idea. So what we're going to do is we're going to look at the execution time of a fraction. And this is the fraction of the execution time spent on predicted important bottlenecks with the different mechanisms. So you can see that ACS and FTP spend about 50% of the execution time on predicted important bottlenecks, critical sections. BIS increased that to 80%. You can think of this as the utilization of the large core also, right? 80% of the time you're executing something on the large core, which means that you're actually utilizing the large core more with BIS because you're identifying more bottlenecks, clearly barriers, other stuff like pipeline parallelism. So this is good. This is one metric. But of course, this doesn't tell you whether you're doing the right thing on the large core, right? You may be executing something on the large core 50% of the time or 80% of the time, but what fraction of it is right? Meaning what fraction of it is really the bottleneck that's bottlenecking the program? And that's this fraction, basically, actually critical. Of course, determining this dynamically is not easy. So what we do is this is all offline analysis of a program. What you do is you run the program backwards and figure out what is the bottleneck at a given point in time and how you'll really accelerate it. So doing this study is not really easy. You have to go through the program backwards. If you do a forward pass, you need to do a prediction clearly, right? So actually critical part is actually not bad, as you can see. So if you look at so you can now if you know this information, actually critical path, you can have 2 metrics. Coverage is the fraction of program critical path that is actually identified as bottlenecks. And you can see that ACS identifies about 39% of the program as actually critical, which means that it misses a lot, right? And BIS increased that to 59% over here, which means that it still misses a lot, but it's better than ACS. So this is the coverage of the critical path. We're not covering the rest. The rest may or may not be in critical sections. The rest may be in the parallel part. I don't know. That needs more analysis clearly. But even in these programs, there's a lot more potential, as you can see. That's coverage. There's also accuracy. Accuracy is identified bottlenecks that are on the critical path over total identified bottlenecks. Clearly, the green parts are actually critical bottlenecks, and total part is the blue part over here. So the accuracy of ACS and FTP is not bad, actually. It's 72%. So only this blue part that's not green is the part that you're shipping to the large core, but you didn't need to because it's not actually critical. Right? So you're really wasting large core resources and energy. You're causing some false serialization. But it's not terrible, you can see. This accuracy is not much better, as you can see over here, right? This accuracy is slightly higher. You're really gaining more from the coverage over here. So you ship this red part to the large core, but that red part is really not actually critical. So you can do better in 2 fronts. You can improve coverage, which means 100% of the time you're executing something that's on the critical path on the large core. And there has to be something on the critical path clearly, right? Although some parts, in some parallel parts, some threads may be equally critical, right? So it's actually very fascinating, I think, to do this analysis. But you could also improve efficiency by getting rid of this red part. You're shipping something on the large core where you're not supposed to, where you don't have to ship it because it's not actually critical. And if you don't ship it, then large core becomes less contended. You get less false serialization, and you improve performance, and you also improve energy efficiency clearly because you're not wasting resources of the large core. In these works, we don't talk about energy efficiency a lot, but later works show that you actually improve energy efficiency significantly also if you do this sort of acceleration. Okay, so let's take a look at scaling results. Before we take a break, I want to finish BIS, bottleneck identification scheduling. But basically, this paper actually does a lot of scaling studies also. This is area in terms of small cores equivalent. You can start with a small chip, 8, and dedicate half of it to a large core. You don't gain a lot of benefit, as you can see. You can have a larger chip, 16 cores, dedicate 4 core equivalent to the large core. You get more benefits. Larger chip, 32 cores, what we've shown. Larger chip, 64 cores. Basically, over time, as the number of cores increases, contention due to bottlenecks increases, and loss of parallel throughput due to large core reduces. So as a result, your performance benefits increase. This is comparison to ACS and FTP over here. In fact, ACS doesn't gain you benefits if you have a very small chip, as you can see. But as you have a large chip, both ACS performance improves. I guess here something happened, I don't know. Maybe the scalability of the program is not large enough anyway. So you don't gain much from 32 to 64, as you can see in these workloads. But compared to ACS and FTP, you gain performance improvement, higher performance improvements. This is an example of having more large cores. Basically, if you have a chip that looks like this, 64 cores, maybe you have 2 large cores and 3 large cores, 1, 2, 3. And this is the speed up that you get compared to baseline asymmetric multi-core. Even ACS speed up increases, as you can see over here. If you have accelerated critical sections and feedback-directed pipelining over here, now you can ship independent critical sections to different large cores. And that performance increased also. Again, keep in mind, these workloads. These workloads are relatively critical section intensive. So false serialization is a problem over here. So you get a lot more performance improvement by having 3 large cores over here. But BIS performance also increases over here, as you can see. Okay, let me summarize. Basically, we've talked about serializing bottlenecks of different types, and they limit performance of multi-threaded applications, and the importance of them change over time. They're not static. And this is a hardware-software cooperative solution to dynamically identify the bottlenecks that cause the most thread weighting and accelerating them on large cores of an asymmetric multi-core. And it's really applicable to critical sections, barriers, and pipeline stages, but it's really applicable to anything that you encapsulate with bottleneck call, bottleneck return, and bottleneck wait instructions. You can do it on any part of your program, I think. Although clearly we didn't test it with any part of the program. And the results are it improves application performance and scalability, and the performance benefits increase with more cores. And I think this is another way of thinking about it is this is really all about fine-grained bottleneck acceleration. And the hope is that it's comprehensive and general enough to do it without any programmer effort. Only what the programmer needs to do in this case is just program with nice delineated critical sections. That's it. Once that's done, a compiler can analyze the program. In fact, the library itself can implement all of these bottleneck wait and bottleneck call. Somebody can code that library, and that what the programmer does gets directly translated into these bottleneck instructions. And you can read the paper for more detail. Of course, we want to improve more, right? Any questions? Yes.
I have a more general question.
Sure.
Maybe my thinking is not, but I feel like every time we see a paper and an improvement in the processor, I feel, oh, this would be great for a server where we have to do a huge calculation.
Yeah.
But I'm always thinking, oh, in my phone or in my computer.
Yeah.
I don't really. Would you say that developing for the two markets is very different, and that you are more oriented to?
I mean, not necessarily. You mean in this area, right? Not necessarily. For example, refresh is a huge thing over here and also over here, right?
So refresh, I
Yeah.
see
On both ends.
Yes, this.
But this particular case. So I guess then the question becomes, in my opinion, where do these multi-threaded programs get executed a lot? And I don't have a very good answer to that, actually. It's certainly done in servers, no question about that. But increasingly, they're increasing over here also. So I think we need a really good study of what do the application profiles are in a system that looks like this, for example. How much of them are really parallelized well? How much of them are waiting for bottlenecks like this? If it's not a problem, clearly it doesn't fit very well. But actually, heterogeneous cores are already here in ARM processors, right? So it may be easier to implement in systems that look like this.
Yeah, when I hear about what they put inside, they say that, oh, we have a small processor to detect how much you're working, and they're making
very simple. Yeah, very simple decisions. We're going to talk about that also. Their goal is to really improve energy efficiency.
Yeah,
in that.
So for example, here you say that we improve the energy efficiency, but if we put it on a server, we don't really care about it. We would rather like more energy.
No, not necessarily, because energy is a problem over there also, right? In the end, if I were a data center operator, let's say, I would really maximize the number of things that I'm executing. And if you reduce the runtime, if you improve the energy efficiency, you can actually run more things. So I think in the end, there is some disparity, no question about that, in a system that looks like this and a system that looks like that. But I think the workload behavior may be similar. Again, I'm not claiming that that's exactly true because I don't know exactly the workload behavior and everything over here. But I believe there are some workloads that are still bottlenecked by these critical sections. But that's a good opportunity for research. Any other questions? Okay, we should probably take a break then. What time is it? Oh, wow. Interesting. I talked a lot about this. Okay, we should take a break until 3 p.m. then. 13 minutes, and then we're going to continue. Okay, let's continue. This is a fascinating topic. I guess I can talk longer, but I'm going to keep some parts short. Basically, we alluded to this, but the question is, can we make even better acceleration decisions? Because even with the previous examples, so going back to this picture over here, this picture is really, really nice, I think. But what this picture is missing is, yes, you may be accurately identifying the program critical path, and you may be covering a good fraction of it, but is the large core really being useful? Is the large core really accelerating the program? There's always that question as well. This picture doesn't answer that question. This picture theoretically or in practice shows what fraction of the program you're covering and how much of that is really accurate. So the next question, of course, is, can we really make better acceleration decisions? For example, if we somehow figure out that shipping this limiter code that we know is on the critical path is not going to improve performance in the large core, we should not do that, right? That's one of the ideas. Maybe we can use the large core for something else then, right? Especially if you have multiple multi-threaded applications, that becomes interesting. And this next work actually tackles multiple applications, both of which may be multi-threaded. So the decisions become more complex that way. So you really need to be very careful in the acceleration decisions. And again, this is not even customizing the cores yet. If you customize the cores, you can actually increase the likelihood of your acceleration decision being better. So this paper actually introduces the idea of utility-based acceleration. Basically, it refines and it tries to understand what is the utility of executing this code on this engine. Should I keep it in the in-order core? Should I send it to an out-of-order core? I think it's a very useful exercise to do. Similar issues exist whenever you really want to run a program. Let's say you've written your program such that it's executable on a CPU or GPU. You still have the same problem, right? You need to somehow understand, is it better to execute on the CPU or the GPU? Again, having a framework that is like this, general, that helps you, or that automatically decides where to execute a code is very useful, I think. And this is doing it for a heterogeneous multi-core engine. So, I mean, you already know some of these bottlenecks. So this is a barrier, for example, as you can see. And between these two barriers, you have some contended locks over here, right? And that becomes your bottleneck. This is your critical path. This is where your critical path starts, right? You can trace your critical path after the end of your execution, and that's how you trace your critical path. And you know exactly which thread is on the critical path if you know the full execution flow. Of course, the key is really predicting what happens, right? So, yeah, those are the barriers over here. You can accelerate the barrier itself also, as you can see over here. Okay. Okay, so these are really looking at the critical paths. These are different bottlenecks. There's also lagging threads, which is really the barrier over here. So you can see that T2 is a lagging thread. This is one way of predicting lagging threads, right? If you somehow, okay, let's do this. Here you're everything is very nice if you have this full picture, right? If you have the full picture, you can run backwards and you know what's the critical path and you can make a great decision, potentially. If you don't have the full picture, you need to predict. And this is one way of predicting, right? This is a heuristic that is proposed and used in this paper. It's also in the BIS paper that basically says, I have a progress fraction for my thread. I know how much work I have in a barrier, and I can calculate how much progress I made to finish that work. And if you know all of that for the different threads, you can calculate the progress fraction, and you can accelerate the thread that has progressed the least. That's the idea, basically. Of course, this requires you to know how much work, for some measure of work, that you have for each thread. And also, it requires you to calculate how much progress you made in proportion to the work that you have, right? So in this case, assume that these threads have, you somehow calculated that this thread has made only 30% progress, while others have made much larger progress. Then you can guess, before coming close to the barrier, that this is a lagging thread, right? So it's a potential future bottleneck, basically. Okay. So that way you can reduce the execution time, because you don't follow this execution, which is really not prioritizing this thread. You follow this execution, which is really prioritizing this thread, executing it on a large core. Okay, so basically you have two problems in this. This paper actually tackles two problems. One is, do you accelerate the bottlenecks or the lagging threads? Because these are actually two different types of things, in a sense. Here, you know, if you go back over here, you kind of guess the bottleneck, right, with thread waiting cycles. But here, there's a different prediction mechanism. It's a lagging thread prediction mechanism, right? And these actually contrast with each other, and the paper has nice analysis related to that. So which one do you accelerate? And if you have multiple applications, which application do you accelerate? That actually compounds the problem even more. So let's take a look at the two application case over here. This is application 1, this is application 2. And it may turn out that this application has lagging threads, for example, and this application has some bottlenecks. And this is the critical path of this application, and this is the critical path of this application after the fact. So if you really want to make a choice, you really need to consider two things. One is the criticality of the code segments. How important are these code segments, and how much speed up do they get when you accelerate them? And you need to do that for both bottlenecks and the lagging threads. So this is an example with only lagging threads, as you can see over here. This is the lagging thread. It's going so slowly. And you need to do this from any running application, right? So the problem is actually more complex, again. So this paper introduced a framework to actually make that decision. I'm not going to go into the details of exactly how it does it, but I'm going to give you the higher level idea. Basically, you want to identify the performance-limiting bottlenecks or lagging threads from any application to accelerate them on large cores. And the key insight is a new metric. It's a utility of acceleration metric that combines speed up and criticality of each code segment. And it does so by constructing an equation, basically. The utility of accelerating code segment C of length T on an application of length T is essentially this. And it's calculated, it's broken down into three things. One is, this is the local speed up of the segment. How much speed up that you're getting on this code segment if you actually execute it on the large core? What is the fraction of execution time spent on that segment? You can actually estimate that also. And this is the global criticality of the segment. How critical is the segment for the entire application itself? And the paper actually finds a way of estimating these nicely. And so you can take a look at the paper. Now, if you actually do that, basically there are two kinds of identification mechanisms. One is the bottleneck identification. It gives you a set of highest utility bottlenecks. And the lagging thread identification, it gives you a set of highest utility lagging threads. And then basically the large core is arbitrated by the utility metric over here. And again, I'm not going to go into details. But this actually considers the utility of accelerating a particular code segment. How much benefit you're getting. So for example, clearly if this is 0, if you're not getting any speed up over here, you're not going to prioritize a segment to be accelerated, right? So there needs to be a measure of how much speed up you're getting. And this measure of speed up is calculated based on some profiling, and you can see the paper for more detail. So it's not an easy problem, actually, in the end. But if you actually do this, and the paper actually compares to a bunch of prior works that I'm not going to talk about, you can see that this is based on bottleneck identification and scheduling, and this is work on lagging thread identification in some way. And these are a bunch of workloads that are examined. You can see that there are 55 workloads. And you can see that utility-based acceleration is better in almost all cases. Not necessarily in some cases over here, but almost all cases it's better. The green curve is higher than the other curves. And you can read the paper for more detail. Because the reason is basically, clearly, bottleneck identification and scheduling doesn't have the notion of utility, right? It has no idea whether large core is really beneficial. And this adds that idea, basically, to the mechanism. If the large core is beneficial, use it. Or use a large core for code segments or threads where you get the most benefit of acceleration. That's the idea. Does that make sense? Okay. This is very similar to what we discussed earlier at some point in a very different context, right? Which is the hybrid memories. What do you allocate in a DRAM cache? Well, one of the ideas that we discussed over there was, again, a utility-based allocation. You pick the page whose utility is the highest, where utility is measured in terms of, again, in some equation, in terms of basically the performance benefit that it gives you in terms of the application itself and the overall system itself. Right? It's similar in that sense. Whenever you need to make a decision of migration, this is also a decision of migration. Here you're migrating code. There you're migrating pages. You need to take into account some sort of benefit of migration. Okay. You can read the paper for more detail. And this was part of Jose's thesis. It's not an easy thesis to do. Okay. The question is, of course, always, can we do better? Maybe you have ideas. Any thoughts? I've given you a bunch of ideas, of course. Clearly, these have not customized the cores at all, right? These are using general-purpose cores still. Any thoughts? If you use FPGAs, for example, you can get much better, I think. Maybe you can customize your critical section execution, and you can have a circuit that accelerates your critical section, right? That sounds good. Or some critical sections you can ship to the in-memory computation engine. Actually, there is a lot of benefit from that. Other people have shown some critical sections benefit from that. Actually, atomic operations are some things that people have shipped to atomic updates, for example. You can consider that kind of a critical section. You're doing it atomically in hardware, of course. Those benefit a lot by shipping it to the processing in memory engine, because if all of the cores are doing atomic updates, for example, you don't move the shared data across the different cores. It stays in memory, and the memory does the atomic updates by itself, right? You can think of memory as a server in that case, right? Memory is really doing the atomic update service to everyone. It's really executing this function. I think you can accelerate a lot of synchronization primitives in memory as well. Okay, any other ideas? Any thoughts?
Is there a possibility that when we are executing a program and any application, then
Could you say it again?
so if we have an application, is it possible that depending on what are the stages done by the application,
Uh-huh.
a particular section of the code can be a bottleneck?
I see. Depending on what other...
Yeah, maybe the branching or...
Yeah, exactly. So certainly. So depending on the dynamic behavior of the input data and the branches in the end, a stage may be a bottleneck at some point, but may not be a bottleneck later on.
So in that case, if a programmer is deciding whether it's a critical section or a bottleneck or not, so in that case, we might have a static thing, may not be a dynamic thing.
Uh-huh.
In that case, maybe having a flag or something add the dynamic behavior might help if accelerating the
Yeah.
code rather than doing for a static.
Yeah. So in all of these cases, it's all dynamic, right? Because you count the thread waiting cycles dynamically. The programmer just says, okay, this is a potential bottleneck.
Yeah, but in that case, actually, we are depending on our prior history. We are not able to decide if so. A programmer knows whether.
Oh, I see. Mm-hmm.
Yeah, so it's like adding the programmer knowledge at the same time adding the dynamic behavior.
I see.
Might helpful in deciding whether the code should be moved to the core or it should to the larger core or it should stay in the smaller core.
Yeah, if the programmer has very good information, I agree with that. Certainly, if the programmer says, okay, this is definitely a bottleneck, then you can take off some of the burden from the dynamic mechanism.
So it's like adding both the things, dynamic behavior as well as programming.
Static behavior. Yeah, I agree. If you can do that, that's good. What else? Any other thoughts? an area that requires a lot of ideas. Okay, so I'm going to go to the next thing, which is really something that we discussed, but I'm going to give you a mechanism for this private data locality. How do we handle this private data locality? Because there's always the question, like we discussed earlier, you have the shared data, now shared data and lock stay in the same core, but now you're pushing the problem somewhere else, which is you need to ship the private data to the server that's going to execute the bottleneck, let's say. This problem actually exists in cases where wherever you want to migrate a piece of code from one place to another place. Right? It doesn't need to happen just with what we discussed, accelerated critical sections. Once we realized that, we actually said there's actually a general execution model in workloads. We call this a stage execution model. And basically, a lot of us are doing stage execution models when we write multi-thread programs, for example. Basically, the key idea is very general. You speed up a program by dividing it up into pieces, right? which may sound too general, potentially. But whenever you do this, you run into this private data or data communication problem. Basically, you split the program code into segments. You run each segment on the core that's best suited to run it. This is actually how you actually specialize computation. And each core is assigned a work queue storing segments to be run. Clearly, there's a lot of benefits. For example, you can accelerate segments or critical paths using specialized or heterogeneous cores. You can exploit inter-segment parallelism this way because different segments are executed in different parts, different cores. And as we discussed, you can improve the locality of within segment data. If you have a segment and if it's touching a lot of data, that locality is improved because that segment is always executing on that core. Right? Like the critical section is always executing on the large core. So you improve the locality of that segment. Non-critical section is always executing this local core. You can improve that's locality is always good. But when you communicate between the non-critical and the critical, that's where the locality becomes bad. So examples we've already seen. Accelerated critical sections, bottleneck identification, scheduling, producer-consumer pipeline parallelism. These are pipeline parallel programs. Whenever you exploit some sort of task parallelism, if you program with task parallel programs, dynamic tasking, for example, that we discussed, there are a lot of really commercial examples of it, as you can see over here. And whenever you can actually think about special purpose cores and functional units this way also. Whenever you want to ship something to a special purpose core, a special functional unit, like a GPU, it's very coarse-grained today, but you run into the same problem, basically. Or even in-memory computation, basically. Whenever you ship something to a functional unit inside the memory, you run into the problem that I'm going to discuss. Basically, at the very high level, a stage execution model looks like this. Basically, you have some program, you chop it into pieces, segments, S0, S1, S2. Hopefully you determine your segments in an intelligent way. You don't chop it into random pieces, right? And I'm going to give you some intelligent ways in a little bit. Actually, you've seen some intelligent ways. And then you basically execute different instances of the same segment on the same core. So you have these work queues and instances of different segments go to the same core. So you will see that in accelerated critical sections go here, right? And non-critical sections are on the different cores. And we have a queue, which is the critical section request buffer. So it really obeys this execution model in the end. Okay, so basically, if you look at the stage execution model, you spawn some segments. So you execute the segment on this core, and then you get to a place where you spawn another segment. Critical section call could be one spawn instruction. And then you execute that, and then that could spawn another segment. So a pipeline parallel program looks kind of like this, basically. You have these pipeline stages, A, B, C, execute on different cores. And first instance of A is here, first instance of B is here, first instance of C is here, second instance of A, second instance of B, second instance of C, ... basically. That's how you fill the pipeline. So clearly, this is good because now you can exploit inter-segment parallelism, and also you can choose the segments such that you have very good locality inside the segment, but you run into problems when you actually move this. So let's take a look at the accelerated critical section example. We already know the key idea. In this case, segment 0 is the non-critical section, segment 1 is the critical section. There are only two segments in this case. And we know that there are a lot of benefits to it by now. Producer-consumer pipeline parallel programs, basically you split a loop iteration into multiple pipeline stages, as we discussed, where each stage consumes data produced by the previous stage, and each stage runs on a different core. In this case, segment n is stage n. So you have as many segments as stages. And the benefit is really stage level parallelism, and hopefully you get better locality. You chop up your code such that a stage has very good data locality inside. Right? In fact, that's how I would parallelize a loop, basically. You have a loop, you have 3 clear parts of the loop that are operating on different types of different data, and I would parallelize, I would figure out the working set that operates on shared data and put it on one core. I would figure out the other working set that operates on another set of shared data, put it on another core, and keep on doing it that way. And that's how I would parallelize. That's how I would maximize the locality and hopefully improve the parallelism as well. So, of course, whenever you have this sort of problem, whenever you have this sort of execution model, you run into the locality of inter-segment data. This is really communication. I would think of these things as communication problems between different segments. And basically you get whenever this core 1 executes this load y, it gets a cache miss because it's produced by the previous core's segment, right? There's a store to y over there. And if you don't directly communicate that early on to this core will get a cache miss for sure. So whenever it gets a cache miss, then the cache coherence protocol enables a transfer of the cache block that contains y into this core. But it's too late because you need to wait for that transfer. Okay, whenever this core executes loads d, it gets a cache miss also because it was produced by a different core, right? And it's in the caches of that different core, so it initiates a transfer. And those transfers are costly. So in accelerated critical sections, basically critical section incurs a cache miss when it touches data produced in the non-critical section. This is thread private data. Non-critical section also incurs a cache miss when it touches the result of the critical section. Right? So a similar problem exists the other way around as well. Okay. Producer-consumer pipeline parallelism, a stage incurs a cache miss when it touches data produced by the previous stage, clearly. So in the end, performance of the stage execution is limited by inter-segment cache misses. And we did a bunch of studies. These studies don't do justice to it, I think. But for example, with ACS, if we eliminate all of the inter-segment misses with some configuration, you get about 10% performance improvement, which doesn't sound that great. But as you scale the system up, you get even more performance improvement. With pipeline parallelism, you get, if you eliminate all inter-segment misses somehow, magically, you can do that in a simulator, you get 20% performance improvement. Now, the good thing is actually, you can come up with a mechanism that captures almost all of that performance improvement, a simple mechanism. I'm going to describe you what that mechanism is. Because these misses are actually easier to handle. And we'll see why they're easier to handle. So let me give you some terminology first. Basically, this is called inter-segment data. You have some cache block written by one segment and consumed by the next segment. Or consumed by some segment later, right? It could actually potentially be consumed by multiple segments, but right now we're actually looking at this model. So in this case, the inter-segment data is a cache block that's housing y and the cache block that's housing z. We also are going to call these generator instructions. The generator instruction is the last instruction to write to an inter-segment cache block in a segment. So we know y is an inter-segment cache block because it causes communication between these two segments. And the last instruction to write to the cache block that contains y is the store over here, right? Of course, there might be multiple last instructions depending on the branching that happens in the previous segment, right? If you have an if, then else, there might be two instructions that are writing to y. So those are both generator instructions. Here, the store z is the generator instruction because it produces this inter-segment data. So basically, the key observation and idea in this paper is the set of these generator instructions is stable over execution time and across input sets. Whenever you are communicating between these segments, the data may be different, but what generates the data stays constant. So these store instructions always generate the inter-segment data. What does this mean? This means that there may be no predictable patterns in the data. So whenever you're communicating between this and this, you're really not communicating blocks A plus 1, A plus 2, A plus 3, A plus 4, A plus 5. So a prefetcher may not be able to capture that. But you know exactly which instruction is generating the data. So there might be no pattern to the data addresses, but there is definitely a pattern in terms of which instructions are generating the addresses. That's the idea basically here. So that set of generating instructions is stable. And the idea is really very simple at that point. You identify the generator instructions, and you record the cache blocks produced by the generator instructions. And before you initiate the next segment, you spawn the next segment somewhere, you proactively send such cache blocks to the next segment's core, such that when the next segment starts executing, hopefully the data that's needed is also there in the core. That's the idea. And that's called data marshalling. It's called data marshalling because it's really data marshalling in the end. This is what a programmer would do. If you actually want to send a function to a server, what you normally do is you identify the arguments to the function, right? Whenever you're programming a distributed system, that's what I would do. The server is supposed to execute a function. As a programmer, what I do is I identify the arguments and I marshal the arguments. Right? That's the idea. Here, the marshalling is not done by the programmer, it's done by someone else, which is what you will see. And in this case, again, it's a hardware-software cooperative mechanism. It's done by the compiler and the profiler, basically. Again, you can come up with a pure hardware version of it. Actually, in this case, the pure hardware version is not that hard. It adds a little bit more overhead. It could potentially be more accurate, actually, because it could dynamically adapt to the changes in the control flow, for example. But we didn't do that. We said, again, a compiler is probably an easier place to do it. A compiler and profiler identifies the generator instructions and inserts these marshal instructions, which are these special instructions that basically send the data earlier before the segment gets launched. And again, a programmer can also do this. No question about that, right? A programmer, whenever you introduce instruction in the ISA, the programmer can use it also. So you can have support for the programmer too. And then you generate a binary containing these generator prefixes that mark the generator instructions and these marshal instructions. In the hardware records the generator produced addresses and marshals the recorded blocks to the next core. So it's a very simple idea. I'm going to give you how it operates. So let's take a look at the compiler pass. Basically, there's a profiling algorithm. It doesn't have to be a profiling algorithm. You could do actually binary analysis also. In this case, we did a profiling algorithm because profiling is not so hard. You run the program once. You know your segment boundaries. You know exactly what the segment boundaries are in bottleneck call and bottleneck return, for example. If you have CS call and CS return, you know exactly what the segment boundaries are. Whenever you have a pipeline parallel program, you know exactly your pipeline segment boundaries are, pipeline stage boundaries are. You know the pipeline boundaries, and you run the program and basically profile the program and figure out what is inter-segment data. Basically, it's data that's needed by one segment and produced by another is definitely inter-segment data. You can easily identify that. And then after that, you go back and figure out what is the instruction that wrote to this data, cache block, basically. So, and then you mark it as generator instruction. That's the idea. And if there are multiple generator instructions during the profiling run, you mark multiple of them as generator instructions. Right? Okay. And then you need to insert these marshal instructions. So marshal instructions actually identify two things. First, when to send the data produced by the generator instructions, and second, where to send the data produced by the generator instructions. So when to send is basically whenever the marshal instruction gets executed. So you may place the marshal instruction strategically in the code so that you minimize the latency. Ideally, you want to cover the latency of transfer. Basically, there's a latency of transfer of the data. There's a latency of launching of the segment, right? Ideally, you want the data to be in the destination core immediately when that segment starts executing in that core, or when the instruction in the next segment needs that data, right? Okay, you can time it, but anyway, I'm not going to go into detail of where exactly this is inserted. This is similar to inserting a prefetch instruction, but much easier, because you know that the segment is going to be launched. Okay, this next one is where to send the data. Here, you somehow need to know which core is going to execute the next segment. So basically, here you need to have some sort of translation mechanism, because clearly when you generate the code, you don't know the physical allocation of the segment to a core, because segment may be executed somewhere. You know exactly which segment you're going to communicate with, assuming that you've done the profiling right, if your profiling is accurate. You know exactly which segment, but you don't know which segment, which core that segment will execute on. So you really need to have a translation table somewhere that basically maps the segment to the core, physical core ID. And this is done in some cases, basically. It's very similar to how virtualization is done. Okay, so assuming that you do that, you can do the marshalling also. So now let's take a look at what's the cost of this. Basically, you need a profiler or compiler that identifies generators and stores the marshal instructions. You need to change the ISA. You need to add a generator prefix that can be associated with a load, with any store instruction. And you need to add marshal instructions. And the library and the hardware binds the next segment ID to a physical core, such that whenever you have marshal to segment 1, you know exactly which core to send the data to. In hardware, you will need to add some more hardware, basically, which is the marshal buffer. This marshal buffer stores the physical addresses of the cache blocks that are generated by the generator instructions, which are the cache blocks that are to be marshaled. And in our workloads, we saw that 16 entries are enough, but actually there are some workloads that need more. So if you have more, the better, of course. And of course, you need to have the ability to execute the new instructions, no question about that. But you also need to have the ability to push data to another cache. Basically, some other now we're really it's not prefetching from the core that needs it, but you're really pushing the data to the core that needs it. So you need to have this mechanism in the caches. So let's talk about the advantages and disadvantages before we talk about the results a bit. So it turns out this actually leads to a very timely data transfer. You can push the data to the core before it's needed. You can say, okay, why don't we actually have a prefetcher in the core that actually will need the data? Now it turns out that doesn't work very well. This paper actually builds on some prefetching mechanisms because prefetchers identify based on identifying patterns, as you know. And here, it turns out there are no patterns in the data. You're not getting address A plus 1, A plus 2, A plus 3. That doesn't happen in this case. It's really, you get an arbitrary sequence of cache blocks. Basically, this data marshalling works really well because it identifies generators of that patterns as opposed to patterns themselves. Now, whenever you actually execute that instruction, you can actually send the data that's produced by it. Right? You don't need to know the address because prefetching relies on predicting the address. There's also another reason why prefetching doesn't work. Prefetchers need information to get trained, right? They need some history. Here, you marshal sometimes 3 cache blocks or 4 cache blocks. And it's too short to train a prefetcher. Even if there was some pattern over there, it is too short to train the prefetcher, and the prefetcher may not be effective. I will show you examples showing that on average there are 5 cache blocks, I think, if I remember correctly. And again, this is low hardware cost. Basically, because we don't do everything in hardware here, profiler marks the generators, there's no need for the hardware to find them. But I think actually finding these in hardware is not that hard. You basically need to see it a few times. Clearly, this has disadvantages also. Requires profiler and ISA support, and it's not always accurate. Because it's based on profiling, the generator set is somewhat conservative or aggressive, depending on how you would like to think about it. Meaning that you can mark a lot of things as generators. If you have a lot of branches, for example, in one segment, and a lot of possible store instructions are writing to this inter-segment data, all of them may be marked as generators. And if you're executing them a lot in the previous segment, all of that data that's generated will be marshaled to the next core, but some of it may not be needed because there's only one last writer. Right? You really want to mark the last writer, but you don't necessarily know the last writer if you have a complex control flow, because you don't know where the control flow will go. Right? That's the idea. Of course, you can optimize this a bit more, but we didn't do that optimization. Okay, but it turns out this is not a large problem because the number of inter-segment blocks is actually small in the end. They're on the critical path, but they're small. Okay, so it has very similar issues. Basically, if you're not accurate, this is an inaccurate prefetch in the end. You generate the prefetch in a different way, but it causes pollution at the remote core. It causes wasted bandwidth on the interconnect. So it is all the downsides of inaccurate prefetches. And the accurate prefetches and timely prefetches have all the upsides of accurate and timely prefetches. Clear? Any questions? Okay, so hopefully this is simple and nice. So let's take a look at the simple and nice model applied to accelerated critical section. So as I said, accelerated critical section is a special example of state execution. You have 2 segments in this case, non-critical section and the critical section. Non-critical section gets executed in the small core, critical section gets executed in the large core. And assume that we mark the generator instructions. This is the generator instruction, which is the input to the critical section, as you can see. and we insert a critical section call, which is really the Marshall instruction. We're going to use the critical section call instruction as the Marshall hint. We're going to add a Marshall buffer to all of the small cores. What we're going to do is basically when the small core is executing, it executes a generator instruction. The generator instruction produces an address, and the address is placed here. And when you get to the Marshall instruction, which is the critical section call, this Marshall buffer will automatically do the following. Basically, you will go through the Marshall buffer. You will access the L2 cache, or whatever cache is the most up-to-date, with the address. And you get the data and send both the address and the data to the destination core's L2 cache. Right? Not just the data, it's also the address clearly. Right? You need to know where to write the data clearly. Okay, that's the idea basically. So it's very simple. So you do it for every entry in the Marshall buffer, because the Marshall buffer is filled with the generator instructions over here. That way, you can send the thread private data nicely to the large core, and you're overlapping the latency of the send to the latency of launching the next segment in the large core. You could decouple the critical section call instruction from the Marshall instruction, depending on where the generator instructions are, right? Clearly, you can do the Marshall first and then do the critical section call later. Okay, and hopefully, when this load Y executes, it gets a cache hit over here. If it doesn't get a cache hit, hopefully the data will arrive soon. So you've covered a fraction of the transfer latency. Okay. So if you do this on critical sections, it turns out you get almost close to ideal. So this is the ideal, meaning that you eliminate all of the inter-segment misses. And in some cases, actually, it turns out, for example, PageMine is very much bottlenecked by these inter-segment misses. Some applications are also somewhat bottlenecked by inter-segment misses. Most applications don't matter, as you can see. But on average, you can get very close to the ideal. In cases where you don't get close to the ideal, it's because the table size is not enough. So there's an analysis in the paper that shows that your Marshall buffer size should be larger if you want to get even closer to the ideal, which makes sense, right? Any questions? Hopefully this is obvious. Okay, so the next one is actually pipeline parallelism. Again, this is another stage execution model. Here, we're going to assume symmetric cores, the same cores. We're not even accelerating the segment that has the lowest throughput. Basically, segment 0 is executed on core 0, segment 1 is executed on core 1, segment 2 is executed on core 2, ... And we identify the generator instructions, as you can see, and we put the Marshall instructions over here. We're going to add Marshall buffers over here. So when you execute segment 0, you get the generator instruction, you put the address into the Marshall buffer. When you actually execute a Marshall instruction, you take the address. In this case, there's only one, but actually you may actually fill it with multiple addresses clearly. For each address in the Marshall buffer, you access a data cache, you get the data, and you send the address data packet to the destination core. And the destination core gets it. And then when the destination core executes the instruction that needs the data, hopefully it gets the cache hit, right? So that's the beauty. Okay, so in pipeline parallelism, actually, this is more effective. In our applications, it turns out this is more of a bottleneck, inter-segment cache misses. You can see that there's 16% performance benefit, which is very close to the ideal again. Yes? Yeah, that's a very good question. In our experience, in almost all cases, it's in the L2 cache because there's not enough pollution, basically. And there's essentially not enough pollution that happens. But it's certainly, it may happen that it's not also, right? Exactly. It depends on the segment size, how much data you touch over here. It may also depend on if you have a prefetcher, if it's polluting your cache. Yes. So it's not guaranteed. There's no guarantee, for sure. But you can, of course, think about improving these designs as well, right? Okay. So I've given you this. Okay. It's always good to, whenever you do prefetching, and you'll do this in your lab, actually, it's always good to look at 3 major metrics: coverage, accuracy, and timeliness. And usually, it's very hard to get a prefetcher that is 100% accurate. Run-ahead execution, for example, which we discussed, which was my PhD thesis, its accuracy is on the order of 90 to 95%. And so it's a very accurate prefetcher. The way it gets its accuracy is executing the program itself. Right? Whereas if you have a pattern detecting prefetcher, it's very hard to get 100% accuracy, actually. If you're getting 80%, you're lucky. And there's always a trade-off between coverage and accuracy, meaning that you can cover more by being more aggressive, but because you're more aggressive, your accuracy is lower. What does aggressive mean? Aggressive means you're actually sending many prefetches, right? We discussed this in the prefetching lecture. Like you can always, if your access pattern is A plus 5, A plus 7, A plus 13, it's not perfectly regular. But if you actually, whenever you access A, if you prefetch 13 things, your coverage is 100%, right? But your accuracy is not very good. Okay. So in this case, this is a nice prefetcher, data marshaller, let's say. And it gets high coverage of inter-segment misses. You can see that the coverage is almost 100% in ACS. In the pipeline parallel things, pipeline parallel programs, it's actually 90%. I think you can improve this actually by better program analysis. By basically identifying the generated instructions better. Because we rely on profiling, sometimes we miss some generated instructions. That's the downside of profiling, right? If you do program analysis, you can actually cover this. So I think you can get your coverage to 100% in both cases. But of course, your accuracy is not as high. Because we rely on profiling again, but maybe program analysis will have the same problem. Basically, you can see that the accuracy is about 60% here. Its accuracy is about 50% over here. Which means that you may have a pollution problem, right? You may actually be prefetching or marshalling data that you don't need in the other core. But that actually doesn't impact performance a lot because only 5 and 6.8 cache blocks are marshaled for the average segment. So here you're marshalling 5 cache blocks. Here you're marshalling 6.8 cache blocks on average. This is average, of course. And timeliness is also very good. Basically, timeliness is measured. There are multiple different ways of measuring timeliness, of course, but one way of measuring it is whenever I need the data, is it in the cache? Right? Whenever I need this inter-segment data in the next segment, is it in my cache? And you can see that more than 80% of the time, it is true. More than 90% of the time, that answer is yes, which is very good timeliness. But that's a very binary way of measuring timeliness, right? Is it in my cache or is it not in my cache? Well, maybe it's somewhere in between, right? Somewhere being transferred. So there's a less binary way of measuring timeliness, which is what fraction of the time has been covered. But of course, that leads to other issues, which is you need to define a baseline time, right? So this binary way has its benefits also. But if it's as high as like this, that even with that binary way, the other metric will only get better, right? Because some other cache misses, even though they may not be already in the cache, they may be in transfer. So the latency that you're going to experience on those will be lower than what you would experience if the prefetcher weren't there. Okay, so basically this is also timely. So basically high coverage, high timeliness, accuracy is middle of the road, but it's not a big problem because you're not actually prefetching a lot of blocks. Okay, so actually I like this idea a lot because this is an idea whose benefit will improve over time. As these stage execution models will increase, its benefit will increase. Why? Because as you add more cores, you're basically dividing those cores into more stages, and you get more communication between more cores. As your interconnect latency increases, again, you get higher latency transfers. This benefits. This idea will overcome those latencies. And as you get larger private L2 caches also, this idea will become more beneficial. This may not sound intuitive, right? Actually, this is a great exam question in general. I'm not guaranteeing that I will ask that question. But there's a reason. The reasons are here, otherwise I would ask you this question right now. But basically, all of these lead to higher improvements. So let's take a look at the reason. Basically, inter-segment data misses become a larger bottleneck with all of these. Why? When you get more cores, you get more communication. And fundamentally, these inter-segment data cache misses are really communication misses. You cannot have a larger cache and cache these misses, right? Because they're caused by communication between different cores. Fundamentally, it's not a cache, I don't want to say, it's not a locality miss. It's really a communication miss. So more cores lead to more communication. If you have higher interconnect latency, you get longer stalls due to communication, so a more effective prefetching mechanism will lead to better performance improvement. And this is the last one over here, which I kind of alluded to basically. If you have a larger L2 cache, it will not benefit you with this sort of misses, right? With these inter-segment data misses, you can make your L2 cache infinite, you will still get these intersegment misses. Because they're not really cache misses. They're really misses that you get because they're not communicated to you in time from some other core. And as you actually make your larger cache larger and larger, you're going to get rid of misses that are locality misses. And these misses will be the bigger bottleneck. So you can argue that I don't like having large caches in general because I think that's not a great way. But even if you have large caches, these communication misses remain. Caching cannot capture it. Okay. So there are other applications of this which I'm not going to go into, but these can be applied to other stage execution models. There are many of them that are proposed. Clearly, some of them are actually employed. These tasking models are really stage execution models. If you do dynamic tasking, Intel threading building blocks, for example, Silk is one of the earliest ones. I guess it's a multi-thread programming model. If you haven't looked at it, you can look at that. Special purpose remote function units, as these increase, this can be applied. There are also some academic proposals that move threads, migrate threads to maximize energy efficiency, for example. Those are also actually stage execution models. For example, this computation spreading, it's an interesting idea. What it does is it divides the code into system code versus user code, and system code executes on cores that are specialized for system software, essentially. And that's another way of actually really improving performance and efficiency. And this is really stage execution. Whenever you do a system call, you go to some other core, right? Okay. And also, it can be an enabler for more aggressive stage execution, right? Because now you're lowering the cost of data migration. And whenever you do remote execution of a code segment, you need to migrate data, no question about that. And if you actually, as you go finer and finer grained, these become a bigger and bigger bottleneck. Because now you have finer grained tasks, and they become more feasible, because now you can enable more finer grained parallelization. So if you actually imagine a future that's extremely heterogeneous, you really want to chop up your program into finer grained pieces and execute each fine grained piece in different accelerators, and you orchestrate the execution on those accelerators. In the end, what will remain is the communication between those accelerators, right? Of course, you will need to have a mechanism to hide the communication latency. And hopefully this communication latency is easier to hide. Okay. I think I don't need to summarize it over here, but let me see if I have anything else to add over here. I think I've said all of this over here. Any questions? No? Is it interesting? Okay, that's good. I see hope. So I think the good news is these are private misses, and these are easier to handle. People have actually tried a lot to predict which shared data you're going to touch in a critical section, for example. And that's not easy to handle. You will not get accuracy results and coverage results like what we've got and what I've shown you over here. The results over there are very, very low. Because then you're trying to really predict what you're going to touch. It really becomes a prefetching problem. Here, really, it's a data marshalling problem. That's why we don't call it prefetching in the end, although prefetching metrics also apply. You really have some information about these communication misses, whereas the other ones are really things that you're going to access. It's very similar to another caching problem, basically. Because communication misses are easier to handle. But they are important to handle, basically. Okay, I guess in the remaining time, I'll very briefly talk about some other uses of asymmetry. These other uses will be energy efficiency, for example. Actually, this is a paper that is relatively old. And when asymmetry for multi-core was proposed, it was really proposed for energy efficiency in the end. And you can see that processor power reduction. And ARM Big and Little was being developed also during that time. And the basic idea is very simple, very similar. It's, again, single ISA heterogeneous multi-core. The idea is to implement multiple types of cores on the same chip and monitor the characteristics of the running thread. For example, you sample energy performance on each core periodically, and you dynamically pick the core that provides the best energy and performance trade-off for a given thread phase. And best core, of course, now depends on the optimization metric that you want. And clearly this is a nice idea, but it's really, the goal is really energy optimization for a single thread in this case. You're really not optimizing a multi-threaded parallel application. So it has its application. So this is from the paper, actually, maybe the journal version of that paper, which basically says you already have these multiple cores. If you're a company like Alpha, which doesn't exist anymore, Digital Equipment Corporation, basically, you have these different cores that you designed over time, right? EV4 is Alpha 21, I guess 064. EV6 is 21264. These are different cores. This is a very simple in-order core. This is a sophisticated out-of-order core, and it's a huge out-of-order core. Why is it huge? Because this was designed in 1990s. This was designed in late 1990s. This was designed in 2008 or so. It never saw the day of light, because whatever. Okay, and you can see that they all have different power and performance characteristics according to this paper. Actually, Intel paper has different results, as you can see, right? For example, here, these folks say that the peak power of a very simple in-order core is 5 watts, whereas the sophisticated out-of-order core is 93 watts. Average power is here 4 watts. Average power is 46 watts. Performance is 1 here, normalized, 2 here. Actually, this may be similar to the Intel paper. We're going to get back to that, right? Basically, here, there's a 20x difference in the peak power. There's a 2x difference in performance. So the performance is costly, actually, as you can see. You need to be careful in terms of when you want to really improve performance, of course, you want to get that 2x, but it comes at a huge power cost for a single thread. And these folks say that if you already are a company like this, you can actually stamp out these cores like this. Of course, I don't think it's that easy because you need there's an interconnect over there also. But assuming that these cores exist on the same chip, now you can enable different trade-offs. So this is one application. Okay, there's also this EV8 is 80 times bigger, but provides only 2 to 3 times more single-threaded performance. So it's 80 times bigger. Interesting. In the same technology node, everything is scaled to 0.1 micron here. Okay, this also shows the instructions per second for a given application over time, and the best core in terms of energy, and best core in terms of energy delay product. So if you know the execution profile of an application, you can determine this. And you can see that instructions per second is different for different cores, clearly. But there are some phases where the cores are very similar to each other in terms of even performance. So maybe you somehow identify those phases. If you're optimizing for energy, you pick the core that is most efficient for energy. You can see that they've done some studies. This is based on their data. You can see that much of the time it's EV6, but a good chunk of the time it's EV8, and sometimes it's EV4. I guess poor EV5 is only in this point. And in terms of energy delay product, it's either EV6 or EV4. So you can actually, depending on the optimization metric, you can pick the core that you want to run this thread on. So it's phase-based optimization. You basically keep some history, figure out which core is doing well, and then ship the phase, ship the next phase of execution to the core that you expect will be doing well for that metric. Of course, I think it's a good idea overall. The ARM Big and Little does something like this. Clearly, it gives you more flexibility in energy performance trade-off. It can execute computation on the core that's best suited for it in terms of energy or energy delay product. You can do it for performance also, but just pure performance is hard because clearly some cores are better than others. Even though in some cases they may be very close to each other, still there's a very little difference in those phases. But of course there are disadvantages and issues in these ideas, and it's similar. These disadvantages are similar to all of the disadvantages of heterogeneity as well. So whenever you want to have an incorrect prediction, you get the wrong core, you get reduced performance or increased energy. There's overhead of core switching. That's true for all migration designs. You get the disadvantage of asymmetric CMP, multiple cores. You need phase monitoring and matching algorithms, different from what we discussed for multi-thread applications. Here you need to monitor the phases somehow. This is actually interesting. We can have a lecture on phase monitoring, understanding what phase of a program you're in. But most of these rely on the execution of a program to be stable for some time. If that's not true, then you may actually do the migration decision your migration decision may end up not effective. And there are a lot of questions over here that I'm not going to talk about over here. Okay, so more generally, asymmetric versus symmetric cores. Let's pull back a little bit. We've been talking about asymmetry versus symmetry, right? Clearly, asymmetric cores can provide better performance when thread parallelism is limited and can be more energy efficient also because you can schedule computation to the core type that can best execute it in terms of energy. But there are disadvantages also. There are lots of disadvantages of asymmetry in general. So you need to design more than one type of core. Is that always true? That's not always true because if you do dynamic voltage and frequency scaling, you get some asymmetry. Or you can dynamically scale the structures of a core. That gives you some asymmetry also, right? Clearly, scheduling becomes more complicated with asymmetry. Again, no question about that. Asymmetry has always some cost. What computation should be scheduled on the large core? Who should decide, hardware versus software? I think these are all open questions also if you want to develop your new ideas. And again, this is also important. Managing locality and load balancing can become difficult if threads move between the cores, especially transparently to the software. Right? How does the software interact with these cores if you're doing this hardware-based movement? And cores have different demands from the shared resources as well. So in the remaining time, let me briefly talk about something that we briefly talked about earlier. But there are also multiple ways of achieving asymmetry. This is not the comprehensive picture, but I want to point out static ways and dynamic ways. So static ways means that type and power of cores is fixed at design time. And there are two approaches to designing faster cores. One is you can have high frequency. That's relatively easy. Basically, fundamentally, some cores are higher frequency, some cores are lower frequency, right? That's not so hard. Or you can build a more complex, powerful core with an entirely different microarchitecture. Right? That's what we've been assuming with the large core and asymmetric multi-core. But there's also some natural asymmetry, right? You may have chip-wide variations in frequency. Because of process variation, not all parts of the chip you can operate at the highest frequency. So you actually bend the cores in terms of what frequency and what voltage you can operate them at. And naturally, everything may be heterogeneous to begin with. This is very similar to the refresh rates that we talked about, right? Refresh rates are heterogeneous because of natural process variation. Maybe core frequencies and voltages are also heterogeneous. And people actually exploited that. The thread motion, thread migration paper actually talks about that. I think a more flexible substrate is clearly a dynamic substrate, right? Static substrates always have the problem of how do you map some computation onto the static substrate. And you cannot change it. You can only move the computation somewhere else. But dynamic substrates adapt, meaning type and power of cores change dynamically. And there are two approaches to dynamically create faster cores also. One is you can boost the frequency dynamically within a limited power budget, of course. You're always limited by the power budget. Or you can combine small cores to enable a more complex, powerful large core. And we briefly discussed this. This is not an easy thing to do, actually, because you need to have glue logic. You need to have additional overhead. And there are two approaches to this also, actually. One approach says, fundamentally, I'm going to design a simple core, and I'm going to add glue logic to merge those cores to be a larger out-of-order core. It turns out, I think this is very difficult. You start with a simple core. If you want to merge those cores, it's going to be difficult to achieve the performance of a large out-of-order core to begin with. Because merging those cores, by nature, you're distributed across those cores, and you really need a lot of communication to enable a much larger core. And you will never get close to a core that's already designed for out-of-order execution to begin with. And there's actually a very good paper that talks about, it's called Core Fusion in ISCA 2007, that tries to do this. And there's a lot of complexity involved in it. Yes? No, not in the product. There's a lot of complexity, basically. I don't think any of this is done. Well, clearly, boosting frequency dynamically is done, but this part is not done. I think the other approach, well, I guess that's the third approach, is you start with the design of a large core, you optimize it for the large core, and you enable partitioning of it. I think that's an easier to do approach, basically. That's the morph core approach in Micro 2012. You have a very large core that can do high performance out-of-order execution. It's designed for that purpose. And you enable a way of really partitioning it or multi-threading it, another way of thinking about it, right? That's easier to do than this approach over here. But both are fascinating, I think. Both are fascinating to think about. And in the end, these enable dynamic heterogeneity. And that could be very useful because now you can dynamically say, basically, you get rid of this dedicating a large core, right? Large core can become small cores when you need it, or it can become a large core when you need the large core performance. That's the idea. And more core paper I would recommend is in Micro 2012, and it shows that there is little overhead when you start with a large core and partition it to many threads. I'm not sure if that approach is done in products yet, but that's an easier to adopt approach for sure. Okay, I think we're right on time, and that's the end of the lecture. Any questions? Okay, if not, have a good weekend. I'll see you next week.